Hello, everybody, and welcome to the 9th session of the RQI-Online 2020-2021 conference. Thank you very much for coming this morning. Hopefully we will have, again, these 2 weekends are shifted in time for our friends in Europe and in other areas, because North America is the first switch into daylight savings time. But yeah, hopefully we will get at least we get 25 people to begin with. So let's begin with it. Our first speaker today is Professor Stefano Liberati from CISA. It's a pleasure to have you here. He's going to talk about 3 small lessons from analog gravity. Great title. Stefano, floor is yours. I will give you a 5-minute warning. Yeah, go ahead.
Okay. Thank you. So very nice to be here. I want to thank for the invitation. What I'm going to do today is a kind of bias view of what analog gravity has done and what it can still give in the future. So, analog gravity in general, for those of you that are not so familiar, is basically an analog gravity system. It's a generic system where you can look at most often at perturbation, at excitation over a background, and show that this excitation can propagate like a field in a curved space-time. In this sense, what they are models, condensed matter models, where you can basically reproduce the feature of the dynamical feature of a field, most often a scalar field, propagating on a curved background. In some system, you can even quantize this field properly. You have a proper commutation relation. And in this case, you can even try to use this as an analog of quantum field theories in curved space-time. So in the past, a lot of activity in analog gravity has gone toward understanding this kind of phenomena, Hawking radiation, cosmological particle creation, or other classical phenomena like superradiance have been played a major role. There has been a lot of attention on mode conversion, and a plethora of systems have been used. And I'm sure that today we will hear some very interesting talks about some system. What I'm going to do here, I want to stress what kind of lessons we can learn in a kind of general way from analog gravity. And one point I want to stress is that somehow, beyond the standard lessons that we have learned so far, there could be space for learning lessons about not just quantum field theory in curved space-time, but general prediction or general expectation of what it may happen when you have an emergent space-time, an emergent gravity framework, let me rather say, a framework where really the space-time is a kind of hydrodynamic limit of some more fundamental theory. That is the idea, where it doesn't make very much sense to just quantize gravity in the sense of the metric. It would be a graviton would be the analog of a photon, and so on. So in this kind of framework, can we use basically analog gravity as toy models for this kind of framework and try to understand some deep lessons about how, in this case, things would work for outstanding puzzle in gravity nowadays? Let me start with a brief review, basically. And I will focus in this talk basically just on Bose-Einstein condensate. There are very interesting models, alternative models. I'm just using this one because some of the lessons I want to draw are based on calculation carried on in this system. Analog gravity based on Bose-Einstein condensate is fundamentally based on the fact that Bose-Einstein condensate in some limit behaves like superfluid. They are envisaged in rotational. And basically, you can recover an acoustic geometry. Linearized perturbation propagate as a scalar field, in particular, the linearized perturbation for the velocity potential propagates as a quantum field on a curved space-time if you have a non-trivial flow of the BC superfluid. Basically, the idea is to work, you start with a nonlinear Schrödinger equation describing basically the atoms in the condensate. You have some kind of cell coupling. You do a mean field approximation. And this basically is a mean field approximation. Basically, it's the idea that you're living more or less in a coherent state, which can be described by a classical wave function. You have a quantum excitation over it. And what you can do is that you can insert these ansatz basically into your nonlinear Schrödinger equation. You get a couple of equations, one describing the propagation of the background. You see, this is a classical wave function. And you see these two terms are called anomalous density and mass, and they're basically the back reaction of the quantum excitation over the condensate. And then you have a term which is basically describing the dynamics of these excitations, right? What you can do is that you can basically do a Bogoliubov transformation to introduce new variables, which are basically, if you want, related to the energy, the number density and the quantum potential and the potential, so the velocity, the perturbation in the velocity potential of the perturbation. This is called the quantum acoustic representation. It's basically a Bogoliubov representation where you diagonalize your Hamiltonian in such a way to describe state of quasi-particle collective excitation above this Bose-Einstein condensate. And the interesting part is that they take the shape of hydrodynamical equation, continuity in Euler, modulo this term, which is introducing, derivatives of the field. If you neglect that term, with basically is the linearized, called the linearized quantum potential, you can show, putting together these two linearized first-order equation, that you can get a second-order equation for θ1, and that is basically the dynamics of a scalar field in a curved space-time. The metric over which you propagate is the acoustic metric. And basically, this structure is the same structure you get in any fluid which is envisaged and in rotation. However, you see, the analogy is not perfect, but this is not a minus, it's a plus, that we will see. Because what it's telling you is that, of course, this is okay, but when you have a high frequency for your quasi-particles, you don't have anymore just a relativistic dispersion relation, omega square equals c square k square, but you get a Lorentz breaking correction. Now, this Lorentz breaking correction makes in such a way that basically low energy, you have a relativistic field. At high energy, if you neglect this term, what you recover is basically the dispersion relation of a non-relativistic field, as it should be, because you started with a Schrödinger equation. Now, the first lesson I want to draw is basically a mini review. Is the main lessons I would dare to say that we have learned from analog gravity so far from a theoretical point of view. You see, a lot of motivation to start the analog gravity framework was basically an outstanding problem in black hole physics. This outstanding problem was the Transplanckian problem. The Transplanckian problem has to do with the fact that if you take Hawking quanta close to infinity and trace them back, you easily realize that in the free-falling frame, their frequency, as you look at the frequency at two different instants of advanced time, basically scales exponentially. So that means that given that you have this infinite accumulation close to the horizon in relativistic physics, you will sooner or later, actually very sooner than later, you will hit Transplanckian frequencies. This was an outstanding problem because basically the calculation by Hawking is quantum filtering curved space-time. You have to assume that basically your space-time and your vacuum are well-defined instead up to Transplanckian frequencies. And this was indeed a very strong motivation to do analog gravity. Why? Because in this case, you have a quantum filtering curved space-time, but you have a well-defined UV completion. So of course, you can do a supersonic flow, and in the supersonic flow, you can have basically the generation of a trapped region, and from this trapped region, no sound would escape. So you have the analog of a black hole for sound waves. Now, the lessons we learned was that indeed this UV completion doesn't really affect the Hawking result. The Hawking result is robust against the UV completion of your space-time. Is robust within some approximation. What I mean is that you should be in a regime where there is a separation of scale from the black hole scale, which is set by the surface gravity of the black hole, which in this case is related basically of the gradient of the velocity radially if you have a radial flow. And this separation of scale basically protects you. You need to have this separation of scale. In addition, you have to have that the setting in of your flow that produce the analog black hole produce basically a vacuum state that for free-falling observer close to the acoustic horizon is vacuum. That is basically equivalent to say that you need to have the onset of the Unruh vacuum, which indeed is something you should expect because it's the only non-singular vacuum you can build once you have an horizon, and this is still true if you limit yourself to the phonon dispersion relation, you don't take into account the Lorentz breaking part. Now, also we learned that in this case, what happens is that the horizon becomes stretched. You have really that the perturbation can fill only a given thickness of the horizon. You cannot resolve the horizon pinpoint, and this provides a kind of natural cutoff faults. Of course, these claims, so theoretically, we understood what were the general conditions that make Hawking radiation robust against the UV completion of your spacetime and of your quantum field theory. And then, of course, it is very important that we got also an experimental confirmation of this expectation. I'm quoting here because I'm referring only to BC, basically the experiments by the group of Jeff Steinauer, which very recently published some stronger and I think convincing evidence that there is a region in the emission of an acoustic black hole in BC where really you are in the Hawking radiation regime. But the point I want to make today is that, okay, is this all we can learn from analog gravity? Basically, this is, I think a Transplanckian problem is a very good example of a very successful story. I sometimes hear people saying, okay, but analog gravity, even if you see Hawking radiation in a black hole in BC, in acoustic black hole in BC, that doesn't tell you anything about the existence of Hawking radiation in black holes. And I find that this is a kind of unjust, criticism, because you see, the point is not so much that we have seen analog gravity. That is a very important result, analog Hawking radiation. See, the point is that we have understood how much this is, under which condition this is robust against the UV completion of your theory. So we have learned a very important lesson. And in general, we have seen how general is this phenomenon, how is unrelated basically to the dynamics of gravity. It's really a kinematical phenomenon. And is resting basically on quantum mechanics and causal structure. And it's even with this deformed causal structure due to the UV regime, if you have the separation scale, basically the results survive. I think is a very important lesson that we've learned, thanks to analog gravity. But let me try to do something more. Can we use analog gravity as a toy model of emergent gravities? So we have an emergent spacetime. Can we try to understand the dynamics of this emergent spacetime? Now, the standard objection is, wait a second, I see in the equation you show me, those are not the Einstein equation. This metric will not have a geometrodynamics ruled by the analog of Einstein equation. How it could be? In fact, it doesn't. But the issue is, can we still learn something by studying how the dynamics of this analog metric is ruled by this set of equations? Let me try to do this in the case of the cosmological constant problem. As you know, the cosmological constant problem is basically a problem related to the fact that nowadays we see a cosmological constant which is way smaller than it should be. If you take simply the energy of the vacuum, you integrate and cut off at the Planck scale, you get basically m Planck to the fourth, and you get a huge energy density, which is not what we observe. How can it be that we are wrong by 120 order of magnitude? I think that, for example, again, analog gravity can help in understanding how in some scenario you could be so wrong. So let me try to do this. I want to take, the equation, the first equation that you get from the Bogoliubov-Degenez equation, the equation ruling the background with the back reaction term of the quantum excitation. Can we write this equation? This is not relativistic physics. So can we write this equation as a Poisson equation for the acoustic geometry? Of course, well, the first things you have to find is, first of all, in a Newtonian gravity, what gravitates is stuff with mass. Secondly, you need to find what is the gravitational potential. To give a mass to the phonon, it's not so complicated. You introduce a term which basically introduces soft to U1 breaking, and you have a pseudo Goston boson instead of the usual Goston boson. And you can get phonons with a mass, which will be basically adjusted by this parameter lambda. Okay, and it can be made very small with respect to the mass of the atoms. The second point is that if you want to identify the analog of the Newtonian potential, You can do that because you can, first of all, identify what is basically encoding perturbation in the metric. And you find that these are encoded in density perturbation. Then you can adopt an ansatz, which is equivalent to expand around a flat space-time that in acoustic geometry means that the flow is zero at the lowest level. And then you can basically look at the Hamiltonian for the quasi-particle in the non-relativistic limit and see what is playing the role of the Newtonian potential. And this object, you see, proportional to the perturbation in the density. So now what you can do, you can take this object and put it back in the background equation. And basically, you see, you can take the anomalous mass and density, as I was saying, the back reaction, the way the excitation back react on the condensate, and split them in a part which is associated to some localized bunch of phonons, plus a part which is there, which is the expectation value of these correlators, as you see, of the excitation in vacuum. Now, these are generically non-zero, of course, because the vacuum for the phonons is not the vacuum for the atoms. And you have in general depletion. And what it's getting is that indeed you can cast this equation as a Newtonian, as a Poisson equation. And what you get is that you get for free a cosmological constant. By the way, a negative cosmological constant. And what you get is that if you compare the energy density associated to this emergent cosmological constant to the emergent Planck constant, because this G Newton, you see, is an emergent object, is related to more fundamental parameters in the theory, then the ratio can be very small. And you see is ruled basically by the dilution factor of the condensate. The ρ0 cube in a proper condensate like the one we do in laboratories is much smaller than 1, because you want a very dilute system of atoms to avoid higher order interactions. You can have just 2-point interaction. And so you see, you get for free a very small cosmological constant. By the way, the cosmological constant here is more close to the fundamental scale of the system, is more related to the Hilly length, is the Planck constant, the emergent one, that basically the emergent G Newton that is huge. That is huge, that is very small, and then induce a very large E Planck, which is another interesting point. You can even try to calculate it and show that this is really this is not basically related to simply the free energy. It's not something you could have calculated by the quantum field theory of phonons with a cutoff at the Hilly length, which is the typical microscopic cutoff in Bose-Einstein condensate. It's something that is directly related to the quantum depletion of the condensate. It's related to the fact that the vacuum state of the atoms and the one of the quasi-particle are not the same. They are they are inequivalent. So what we have learned, you see, you learn something, of course, this is not GR, but it's teaching you something. It's teaching you that when you have an emergent space-time, first of all, if you want to know if there is a cosmological constant, you have to compute the analog of the Einstein equation. You cannot predict it a priori. You cannot predict it, most of all, from the effective field theory of quasi-particles on your emergent space-time. Not only the energy scale of this effective cosmological constant is ruled, can be ruled by a very small number that is non-perturbative in origin, which is even more supporting the fact that you cannot get it out of an effective field theory or, for example, from semi-classical gravity. You can do the same things that I did here in the case of a relativistic DC. In that case, you get the equation, the Einstein-Fokker equation, which is basically Nordstrom gravity, which is a theory which was developed in 1913 and was the first step toward general relativity. You get something that smells more like Einstein gravity. Of course, it's a scalar theory of gravity because you have only scalar degrees of freedom, and it has an intrinsic background because it has all the metric are conformally flat in Reisner-Nordstrom theory. And then there is the last lesson I want to discuss, which is the following. You see, another things you may ask yourself is like, okay, I can simulate Hawking radiation in analog black holes. But of course, in analog black holes, nothing forbids me to simulate a region where the hydrodynamic approximation breaks down. What I mean is that nothing forbids you to simulate a region that would mimic a singularity, a region where space-time is not defined for you. Not only you can do that, but in principle, you don't need to kick out atoms of the system. You can always do it in a way that your atoms are not leaving the system. At least in principle, experimentally it's not so trivial. But you see, then there is a question, wait a second, but if this is true, the Hawking partner generated by my Hawking process sooner or later will end up in this singularity, in this region of non-defined space-time. But then, in a certain sense, I will again have a problem that even if I start with a state which is a pure state here on this hypersurface sigma 1, and even if I can track momentarily the outgoing Hawking quanta and the ingoing Hawking quanta, when they get in this region, I have to trace over them. And it seems that here, after the evaporation of the black hole, if I can simulate it, and we will discuss that in the very end, then you will get something that is unitary breaking. But that, of course, is an absurdity. If I have a system of n atoms enclosed in a trap, and whatever dynamics I do, whatever things I simulate, there is no information loss. There cannot be an information loss truly in BC. What is the problem? The problem is that we're assuming that by looking at correlators of quasi-particle, you can fully recover all the information. But if you have a region of non-defined heterodynamical limit, which is tantamount to say that where your space-time is not defined, you have to resort to a different description, to a more complete description in order to track what is going on. So you have to go beyond the mean field approximation that we introduced before. So it is a bit of a technical calculation, the one that I'm going to try to describe in very few minutes. So, but I want to give you the basic idea. So what we want to we consider was a very simple system. Imagine you are able to have a condensate, and you want to keep track basically of the fact that when you have quasi-particle excitation, you want to keep track that they are related to the fact that you are moving atoms from the condensate to the excited part. So you need basically to retain information about some distraction and creation operators for the atoms in the condensate. Now, with the mean field approximation, you cannot do it because at step 1, you define the condensate as a classical object. However, there is a formalism that was developed by Perron and Sosnanger in 1954, which is the one of the natural orbitals. Basically, you describe the condensation by looking at two-point correlation function. And what you do, basically, a condensation will happen when you have a state in which basically you diagonalize them, and these are called natural orbitals, this F function. And when we have that one of this I, let's say 0, is basically almost 1, equal to the number of the total number of atoms, and the other one are basically 0, then you say that you have a condensation. In this case, basically what you get is that you are dominated by one natural orbiter. There is only n0, which is truly non-zero, and all the other are 0. Now you can see that it is possible to show that this is just basically a way of rephrasing things. But if you are careful and you know, I mean, in handling the equation, you can show that basically the equation ruling the mean field can be translated in equation ruling this natural orbital for the 0 state, for the condensate state, which still is of the Gross-Pitaevsky type, plus possible depletion for the dependent terms. So now what you want to do is the following. Imagine now you have a system, and we wanted to initially to use Hawking radiation, but Hawking radiation is very difficult, and this formalism is heavy. So we decided to go for a simpler mechanism, which is cosmological particle creation, where you have that homogeneity of space-time helps you a lot. So what we can do, we can basically, we studied the analog of cosmological particle creation. This is something that in BC is well known how to do. One way is basically to introduce a Feshbach resonance. You can basically adjust in time the scattering length. So we were considering the standard problem, static space-time expansion, static space-time. And with this problem, we analyze the analog particle creation in this formalism where you can track, you see this creation and distraction operators inside have a zero, the distraction or a cross 0, which is the creation operator for an atom in the condensate. Not only, but we also enforced in the formalism that we were defining operators which were conserving the total number of atoms. So that when you create quasi-particle, basically you can really see that you are moving atoms from the condensate to the excited state. So what happens to the correlators is that after you have this period of expansion, you have that the correlation is non-trivial. There is an oscillatory term, which would be there anyway, which is basically telling you that there is always an exchange between excited part and the condensate. And there is a growing part. You see, this is basically Bogolyubov coefficient, this guy. And this must be greater than 1 for having particle mixing, because we want a non-zero term here. And what is happening is that you have a growing mixing, you have a growing part as the particle creation, you move atoms from the condensate and you push it in the excited state. So what is the consequence of it? Is that you can show that at the end, you get a squeeze state relating the initial vacuum with the out vacuum. And this is not surprise because it's true always, even if we do standard quantum field theory in curved space-time. But you see now, these coefficients are describing pairs of quasi-particles, which inside have also the information of which atom from the condensate you move up. And so what is happening is that, yes, I'm almost done. So what is happening here is happening that basically you remove this atom from the condensate to put them in the quasi-particle state, and you create correlations. The correlation between the atoms in the condensate and these pairs of particles, quasi-particle created, you see, if you could make this difference, you get something that is non-zero. And it's non-zero because basically there are commutators stuff, this H0, which is the stuff related to the atoms in the condensate, doesn't commute with the operators associated to number conserving atoms creation and destruction, basically. And you see they are suppressed by N0. And in fact, the lessons that you learn is quite interesting. Basically, what it's telling you is that when you have a process of particle creation, basically you have quasi-particle. The quasi-particle are leading to a depletion of you move atoms from the condensate. The depletion implies that even if you start with a state which can be factorized in atoms in the condensate times atoms in quasi-particle, and you say initially you are in the vacuum of the quasi-particle, the out state cannot factorize anymore. You see, left and right coupled is not just a factorization of stuff in the condensate and stuff and excitation. You have an entangled state. And so what it means that given that if you want to reconstruct the purity of your initial state, you have really to look at these correlators between atoms in the condensate and quasi-particle. Now you may say, given that these correlators are suppressed by N0, which is the total atoms in the condensate, in a cosmological particle creation, which is happening everywhere in the condensate, this is negligible. Even more if you think of the analogy with true space-time. But in a black hole region, the conjecture is that it's only N0 are the atoms in the black hole region that those matter. Those are finite, not only, but if the black hole shrinks, there will be less and less of them. And these correlators, which are ever present between the atoms of space-time and the Hawking quanta, will become more and more important as the evaporation goes on. So when you take the Bogolyubov limit, it's equivalent to forget about the quantum nature of these atoms of space-time. You take a classical expectation value. And of course, the squeezing operator I showed you before becomes a squeezing operator for Hawking pairs. And that is still a unitary operator. But as I was telling you, sooner or later, the ingoing Hawking partner will arrive in a region where space-time is not defined. Or in our analogy, in a region where you don't have the hydrodynamic limit well defined, you cannot define the acoustic geometry. There, the two descriptions are no more equivalent. If you want to deal with the evaporation problem, you have to be able to track these correlators between the quantum degrees of freedom space-time and the Hawking quanta. So in this point of view, you see what is teaching us that information loss problem could be a semi-classical gravity artifact. It could be basically due to the fact that we insist in seeing this preservation of information in a process that unavoidably entangle the quantum degrees of freedom of space-time and what we call quantum matter over it. And in a certain sense, after the evaporation, you wouldn't get a Minkowski with a thermal bath of matter. You will get a highly entangled state within matter and gravity that you can, in some limit, reduce you take an expectation value and you say this is like Minkowski with some matter field, but you would lose all the correlators which are fundamental to recover the information. Now, the last two slides are basically just to tell you that we have done, you see, I was suggesting that the black hole can shrink also in acoustic gravity, and that the relevant number of atoms in the black hole case would be the number of atoms in the black hole region. Basically, what we did to look at this was to analyze the Hawking radiation in a canonical black hole, which is a simple solution of black hole solution in acoustic gravity, and our gravity is this one. Basically, we worked in the limit where we basically were doing the standard calculation of quantum field theory and curved space-time. We were recovering the Hawking radiation. And then we were saying, okay, what happens if I insert the back reaction of Hawking radiation into the first loop of the Jarius equation? They were the same one I used to find the Poisson equation before. Well, you can basically relate them to these number conserving operators and so on, like we did it before. And you see what is basically ruling the back reaction is the correlator of theta 1, that basically is, because theta 1 is basically the field that propagates on the curved space-time. And what you get is interesting, because you get something that is telling you three things. One is that the black hole shrinks, at least in acoustic analog black hole, in canonical analog black hole. Basically, the back reaction makes the black hole shrinks. You have a finite lifetime, which is basically parametrically related to the lifetime associated to the Healy length and to the number of atoms in the black hole region. And if you look at the global effect of depletion, basically what you have is that you see it really scales like the temperature and the number of atoms in the black hole region, as I was telling you, and the value of these correlators at the center of the configuration, which in the canonical analog black hole, by the way, would be, you will have to regularize because it would have an analog singularity as well. But of course, there you can go for a description where they describe the atoms, not the quasipart. So at the end of the day, this is corroborating our point of view, that is telling you that exactly the back reaction is related to the number of atoms involved in the process, which are the one in the trapped region. And if you want to know how we calculated this correlator, basically was to use the standard results for the correlator of the fields in the Uru vacuum when you have Hawking radiation. So I'm at the end of my talk, and my talk, you see, was basically telling you three lessons. One is that is the historic one. We understood that Hawking radiation is UV robust. Two, we understood using the analog gravity as an analog model of emergent gravity, that the cosmological constant is a problem that requires in emergent gravity to really rederive the fundamental geometrodynamic equation. You cannot get it as quantum field theory with a cutoff in the UV. It's far from that, it's very unrelated to that. Lesson three, the information loss problem in black hole could be an artifact of neglecting basically the Hilbert space of gravity in semi-classical gravity. There are questions that require where you can basically not do this anymore. I'm not saying that the semi-classical gravity is not useful, it is, but the information loss problem, if you accept this point of view, of course you can baby universe, which is equivalent to losing atoms for your condense. I'm not saying that this is the answer to the question, but in this framework of emergent gravity, it is very natural to think that it is an artifact, the information loss problem of semi-classical gravity, that really, if you would be able to track the correlation between the quantum gravity degrees of freedom and what you call matter field, quantum matter field, there would be no information loss problem. And I think that this is just the start. There may be many other applications of the sort I just told you. And for this reason, I want to end with an upbeat note that even theoretically, it's not just experimentally, it's very exciting analog gravity. There is still much that can be done theoretically. And I think that analog gravity has still many other lessons to teach us. Thank you.
All right, thank you very much, Stefano. Very nice talk. All right, so now we take questions. As usual, please use the raise hand feature of Zoom if you can. If not, try to be very visible. Raising your hand. All right, we get the first question. Hans-Jörg.
Yeah, so very nice talk.
Thank you.
One thing that always came up in our experiments, and we tried to do, experiments with relativistic quantum fields and look at that, is that for the moment you only look at two-point correlators, and that basically implies that you neglect any interactions in there. So you would only see propagators. You won't see vertices.
Well, okay, we are basically working the approximation where we have only atom-atom interaction. We're not taking higher order term. That would complicate a lot. The correlators, in principle, you can look at higher order correlators. For our point, it wasn't necessary to make the point. In general, what I would expect is that there should be a way in an experiment to see that you have this extra correlation. Not to see this this correlator between the atoms.
We did that.
Okay, that would be very interesting.
And we did that.
We
did that for the systems that have no interaction, for systems that have interactions, and for excitations that have a mass. And we also showed how to extract the fundamental, the fundamental problems of the quantum field theory behind there, like the running coupling constants and things like that. Over the last
do you
years.
look at exactly the correlators between atoms in the condensate and the excitation?
No, we look at the correlators between the fields, between the excitations in the field. So these are really field correlators. These are the correlators
what I was
in
trying
the simulated relativistic quantum field theory.
Yes, what I was trying to say is that it would be interesting to see if in an experiment you can show that there are missing correlators, like in an analog Hawking radiation, in the sense that those correlators between the atoms in the condensate and the quasi-particle, instead of trying to see them directly, try to prove that they must be there as missing part. And that would be was what I was trying to say, which I don't know if it is experimentably feasible.
But we can measure also particle-particle correlators directly. But isn't that a different thing? That if I measure the particles, I measure the microscopic Hamiltonian of the system. If I measure the field correlators, I measure the emerging quantum field theory that I get from the system, and that can be much more directly emerging than just the mean field. I mean, if you look at the Sine-Gordon model or Klein-Gordon model that emerges in this type of fields, you don't make all these you don't have to make all these approximations that you do in the mean field theory.
Yes, of course. No, I see with your point. Of course, yes.
Because that mean field is a very, very classical sense, whereas a strongly correlated Sine-Gordon is very far away from the classical.
Yeah, I know. It depends very much on what you want to see, what you want to try to prove, or what I was trying to argue is that for a problem like to see that there is no information loss problem in analog gravity, basically you have to go beyond the mean field. That is exactly my take home point. Thank you.
All right, thank you very much. Next question, Albert. Albert, go ahead.
Hi, Stefano. Nice to see you.
Hi, Albert. Nice to see you.
Very interesting and stimulating talk. So maybe just some thoughts on how to push some of these very interesting ideas a bit further, in the sense that trying to address some of these difficult questions that you were trying to gain insight about with these analogies. And so, for example, for the cosmological constant problem, so you were here showing, the extreme case where you assume that the contribution to the vacuum energy is the Planck mass to the fourth power, basically. But sometimes the cosmological constant problem is phrased in a sort of slightly milder way, still as a fine-tuning problem, saying, well, let's think of a regime where we think we understand our low energy effective field theory, for example, at the energies of the mass of the electron. And then, you think that maybe you understand your physics there much better than at the Planckian scales. And then you would see that you still need a very large fine tuning, in the sense that you would naturally then get with this massive particle, when you integrate out the contribution from electrons and positrons, a contribution to the vacuum energy of the order of the mass of the electron to the fourth power. And you still see that you have a large fine tuning there. I mean, not.
Yeah, you're right.
But still. So it would probably be interesting to push some of these ideas to look at a case where you have some of these massive excitations, but much lighter that you were considering, where the effective field theory description is still valid. And you try to understand their, these fine tunings in a regime where you think that, your effective field theory should still be valid. And see what happens, for example, there with the standard argument about the fine tuning in the context of particle physics. You see what I mean? I mean, not pushing everything at the Planckian scales where we don't really, and then in your condensate, it's also very different physics. But looking instead at a regime where you think that the effective field theory description is reliable in many respects, and trying to understand there the analog of this fine tuning, which is milder, but it's still a large fine tuning in the particle physics scale. In the particle physics case, for example, the mass of the electron.
I agree. This would be very interesting. But you see, there is another point that I think that would be very interesting. You see, somehow the point is what gravitates. You see, you can compute these energies. It's not that you cannot do quantum field theory on your space-time and integrate and put have an argument to have some cutoff scale. Maybe not in the far UV, as you were saying. But still, the problem is that what determines what gravitates and what not? Why is the depletion part that gravitates and not this other energy that I can compute in principle? See, the depletion, if you want an interpretation, a physical interpretation, is that you have this gas of atoms that is basically over the condensate and is pushing, is giving you a constant effect on your condensate. And that appears as this cosmological constant in your effective equation. But somehow I would like to go deeper and understanding really what is going to enter in your analog gravitational equation and what not. Because otherwise you can compute many kind of energies and then still they do not gravitate. Why?
I understand. Right, but what I was saying is that if you want to, I mean, all this is of course very interesting, and one can learn a lot from this kind of analysis and studies. But what I was saying is that if you want to confront, I think, the more carefully phrased cosmological constant problem as a naturalist problem in effective field theories, then it's maybe cleaner, even for the argument in particle physics, to really discuss everything in a context where effective field theory, we think that effective field works.
Yeah. I agree with you. You can give already an argument without pushing it to the
right.
terra incognita.
Already in particle physics, that's the cleaner argument that one can have about the naturalist, the cleanest argument. So the question would be then try to understand that fine tuning in analog systems like those you were.
Yeah, to see if I see, but still, the point is that there is a fine tuning if you are convinced that that energy ends up gravitating. You see, if that ends up gravitating, then it must be fine tuned to not be as large as you expect, But the point is that maybe you compute it, you don't need to fine tune it because it doesn't gravitate, it can be huge, but simply it's not relevant for the dynamics of your space-time. That is what I was trying to say.
The question is that suppose that you manage, similar to what you were doing, to introduce some, maybe you need two fields with two different masses, one acting as a test field and the other as a source. But suppose that you introduce—
You can do it with a two-phase BC.
Right, and so then you could have one of these fields that could be the analog of these electrons, right? With a slightly higher mass, but still within the effective field theory, the regime where the effective field theory is valid. And then you look at the infrared regime, at energy scales sufficiently below that scale for the other test field, for example, where you in principle can integrate out this analog of the electron field. And then you try to see in a regime where the effective field theory description and Lorentz invariant, approximately in the infrared is valid, try to see the analog of the fine tuning that you would have in the particle physics counterpart, how it plays here.
Yeah.
So the interpretation,
as soon as we can travel, you should come and we will do it.
Yeah, well, why not? Yeah.
You're very welcome.
All right, we have maybe the last question for this discussion, Cisco.
Hello. Thanks.
Hello.
A very beautiful talk. Honestly, I learned a lot about presentation for one thing, but the content was beautiful. I have a question about the back reaction calculation that you were doing. you extracted like a lifetime and kind of, are these extrapolated features like in the Hawking calculation, where
Yes,
you take
basically,
rates
yes,
and you kind of
basically.
just assume that if you extrapolate
No,
back?
no, you have a very good point here. I wasn't completely fair on this. Yes, what we have done, you see, this calculation is valid as long as you have adiabatic evaporation. Now, if you have a large black hole, because you see the variation in the radius in time is shrinking, this is the minus, but you see it's ruled also by the size of the hole. So if you have a large hole, large with respect to what? Basically, you see here you have the Hilly length, and basically these are the standard quantities entering the VC. If you have a large black hole, then this is true. Then this derivation is correct. If you are going toward the end of the evaporation, this is not going to be true. This is true also for, of course, a standard black hole. However, yes, you can do a kind of extrapolation. I was more to have an order of magnitude than what quantities were getting there, you see. Of course, the final T is the fundamental time in the system, which is again related to the Hilly length and the number of atoms involved. This was, but this is an estimate, is an extrapolation, you're right. It's correct because sooner or later, this adiabatic approximation will break down. You see, if this is not true, basically you're not sure you have a thermal radiation. We are using, if you want, the Stefan-Boltzmann law at the end of the day.
Ah, okay. Yeah, I was wondering what aspects of the fully back-reacting equations were being used for this estimate. Is there any hope at doing the full problem?
Well, in principle, differently from gravity, yes, it would be very complicated, but in principle, yeah, the system is fully under control. You should be able to go. You see, we did basically the approximation that initially the system was stationary. You didn't have a perturbation of this canonical black hole. You just had Hawking radiation, and it was in a adiabatic regime where you can, for example, negate the temporal dependence of this correlator and so on. Otherwise, the calculation becomes much more complicated. But in general, I mean, in principle, the formula are there. I mean, if one has to, it's simply that is getting very complicated. Maybe one has to do it numerically.
Yeah. Okay. I just thought there might be something to be learned at just seeing kind of, because this is kind of, you can test some ideas about information loss and whether you think remnants are possible, or whatever your personal flavor is for those things in the analog.
I want to add something, given that you touch it. You see, the information loss problem that we have illustrated would be there even if you have a regular black hole. I mean, imagine that you have a region where instead of getting in a singularity is regularized by quantum gravity, and then, I don't know, you have a bounce or you have a trapped region that exists for a finite time and then evaporates away. As long as you have a region where you cannot do proper semi-classical gravity, then you cannot ignore anymore this correlation between geometry and matter. So what I'm trying to say that even in the case of regular black hole, you may have a problem if you don't track the correlation between the quantum degrees of freedom and the Hawking degrees of freedom, the quantum geometry degrees of freedom and the Hawking quanta, sorry.
Yeah, okay, great, thank you.
All right, we have a final question. So has George again?
I just have a very quick question to this information loss.
Go ahead.
So if I want to reconstruct the information, I basically have to reconstruct the correlators of the emitted radiation. Yeah.
And the atoms of space-time, that means.
Yeah, you have to reconstruct. So even if it's in a simple thing, so that basically means to reconstruct an endpoint function with all its connected parts.
Which
and
is
that's an exponentially difficult problem.
Of course. So in practice,
I cannot do for more than lost. Which if I would use every proton in the universe as a computer, I can probably do it for 50 or for 60 photons.
Absolutely correct. So in practice, it's
and
lost,
I would have to do it for 10
violation of quantum mechanics.
30. Yeah.
Yeah, but that what you're saying is that in practice you cannot reconstruct it. But the point is different from say that there is a paradox because there is a violation of quantum mechanics by gravity. This is conceptually different.
No, but my conceptual question was that what is if I have no means of proving it? Is that still a conceptual problem? I'm not sure.
Well, I don't know, because to me, it's a technical problem. It's a matter of having, I don't know, some.
No, it's not a technical problem. Our universe is finite.
But you see, the problem is that to me, still there is no paradox anymore. But you see, in Bose-Einstein condensate, what is showing, I mean, you know the answer. In Bose-Einstein condensate, there cannot be any unitarity violation. The system is fully quantum. Nothing can violate quantum mechanics in a BC if you don't kick out the atoms. So yes. even a BC, there is a problem that you will never be able to reconstruct fully the quantum state.
Yes,
although,
that's why
you know,
we could
given
show,
that the suppression in 1 over n0, yeah, but remember that there is a suppression of these extra correlators. The higher order are more and more suppressed. So what it means is that probably if you can manage to observe the one that are suppressed by 1 over n0, the number of atoms in the condensate, you're still basically reconstructing most of the state. What I mean is that there should be a way in which you can quantify that you have basically the full state with an error that goes down like 1 over some power of n0. You see what I mean? I don't know exactly how to do it rigorously, but I think you can quantify your error. So for me, it's enough that you can show that this is still a pure state with an error of 1 over n0 squared. You see what I mean? And that for me would be fine. The problem is that still practice. I mean, of course, in reality, for a real black hole, I think that this is a daunting task that nobody can do. But still, it tells you that if you do full quantum gravity and you have matter fields and quantum degrees of freedom, there is no way that there is no violation. Everything is fully self-consistent. Then maybe you are never able to measure it and to prove it practically. I still think that there will be this idea that you can prove it modulo an error that you can control. Thank you.
All right, very nice. Thank you, Stefano, for the nice talk. That was really nice. Thank you again.
Yeah.
All right, I'm going to pause the. All right, our next speaker today is Maxime Jacquet, the St. Andrews, the UK, and also the birthplace of golf, right? So anyway,
all right.
He's going to tell us about entanglement measure for the characterization of Hawking emission in analogous to gravity. So 20 minutes, I'll give you a 5-minute warning. Whenever you want, floor is yours.
Thank you very much, and thank you for having me. It's really great to be back at Relativistic Quantum Information North. Some of the work I'm going to talk about today is actually a follow-up from something I presented back in 2016, at a time at which the UK was still part of the EU, and I think now we are very much out. And most of what I've done and will present today was done, in fact, with Friedrich Koenig at St. Andrews. Okay, so I want to tell you about entanglement and Hawking emission in analogs. And so first, perhaps I should just clarify what I mean by the Hawking effect. And just like everyone else, what I mean by the Hawking effect is this scattering of incoming modes into outgoing modes at an event horizon. And okay, in the canonical example that we all know from 1974, this is a real black hole that scatters incoming modes that are in their vacuum state, and out comes a thermal state. And quite famously, this derivation survives many different problems, including the Trans-Planckian problem, like Stefano was telling us about just earlier. And it also survives being ported to analog gravity setups. So instead of having an actual black hole, you may have just a horizon in a transcritical flow or in a transsonic flow or something like that. And it will still create an outgoing state from incoming vacuum. And the Hawking effect also works if it's stimulated. So if instead of the vacuum at the input, you have say a coherent state, it will be scattered into an outgoing into outgoing modes. And that's really what I mean by the Hawking effect. And in order to understand that, in order to understand how the Hawking effect manifests itself in analog gravity setups, we must ask ourselves what's the motion of waves at the horizon. And there again, we call on the 1970s, and we call on Bill Unruh, who famously explains that the horizon basically separates two regions of space-time, one in which waves can go back and forth with respect to the singularity of the black hole, and one in which waves may only go in one way, that is towards the singularity. And most analog gravity setups, including water waves or Bose-Einstein condensates for sound, have a dispersion relation in which there is a small difference with the picture, the simple picture from the actual gravitational setup. And that is, there is either subliminal dispersion or superluminal dispersion, which means that there is a small correction to the dispersion at large wavelengths. At large scales, sorry, high frequencies. And therefore, very famously for the Bose-Einstein condensate, for example, there can be modes that come from inside the horizon and scatter onto it. And that's in fact where the negative norm mode comes in the Bose-Einstein condensate. And what I'm going to show you today is the optical case in which the dispersion relation is a bit different. In fact, I will show that the dispersion relation is a bit nicer in terms of analogy, direct analogy with the river model of the black hole. So the optical horizon can be created, for example, in an optical fiber by propagating a very intense pulse inside the fiber. And under the pulse, the refractive index is modified. So that means that the velocity of light is modified. And a weak probe wave will itself not modify the refractive index much, but it will feel by cross-phase modulation the increase in the refractive index under the pulse. And if the pulse catches up with the weak probe wave, it will scatter the wave and it will redshift it. Okay, and if instead the probe wave catches up with the pulse, it will scatter and it will be blue shifted. And this blue shift and this redshift were demonstrated in 2008 at St. Andrews. And in fact, I think they were one of the first two experiments on analog gravity together with those of Germain, who will talk just after. Anyway, the point is we have in the optical fiber, we have a dispersion relation and we have a moving pulse. And it's all very complicated to understand if we stay in this reference frame, that of the laboratory. So instead, to make calculations, it's simpler to go to the moving frame, where the pulse and the horizon are stationary. And there we obtain a dispersion relation which looks like this. And I've included one further solution compared with the left-hand side, which is the negative norm mode. And the point is, we have scattering when waves share the same frequency. Okay, and in fact, this is a very interesting topic, because back in 2016, when I came to RQI for the first time, just the same day before me, there was a talk by Bill Unruh. And at the time, he was talking about this recent paper that he had with Ralph and Linda. And he was considering a simple model of the refractive index inside the optical medium. And he was considering a smooth profile for the change in refractive index under the pulse. And this together with my talk, where we had a very complicated model of dispersion, that's the full model for dispersion. And instead of a smooth profile, we had a step-like profile. And from there, at the time, I remember we talked about this with him. There were basically two main routes to be explored with those models. One was using the simple model of dispersion to go and look at effects of dispersion and dissipation, and how this affects the spontaneous emission at the horizon. And I think that Bill, Ralph, and their students, including Sasha Lang, who will talk on the 5th of May, have done wonderful work on this, so tune back in on the 5th. And on the other hand, together with Friedrich Koenig, we went on with our full model of dispersion, and we tried to see, to contrast horizon versus horizonless emission, and to calculate correlations and entanglement in the optical system, something that had not been done before. And this is what I want to tell you more about just now. So as I said, we have we model the change in the refractive index under the pulse as a step-like potential in the refractive index. Okay, and we are in the referential in which the step doesn't move, and I show in the dispersion diagrams in green, in black, sorry, the dispersion relation of the region that's before the step where the refractive index is low, and orange, the region where the refractive index is increased under the step. And we see that as a function of frequency, a horizontal line of conserved energy intersects different times, many different times with the dispersion relation. So which means that as a function of energy, because of dispersion, we have various modes of the field which may scatter into one another. And specifically, we can look here at the bottom right diagram, where on the black line we have four intersection. On the black lines we have four intersection points. That gives us three modes that propagate towards in which light propagates toward the interface, and one mode in which light propagates away from the interface. Whereas where the refractive index is increased, light may propagate only away from the interface. And this is very interesting because here we have one-way motion before the step, and two-way motion, sorry, before the step, and one-way motion only under the step. So that's very reminiscent of the river model of the black hole. And in fact, that's much closer to the idea of curvature of space-time which I have than other systems. And at other frequencies, the situation is very different. And so, and specifically, we have two-way motion or only one-way motion on either side of the boundary. So basically, this tells us that as a function of frequency in the optical system, just like in any other system, we may have a horizon-like situation. So that's the bottom right here, or a horizonless emission. Those are the two that are here on the left-hand side. And this one's a bit more complicated. So let's forget about it. This system, just by changing the energy at which we make our analytical calculation, allows us to contrast horizon versus horizonless emission. And we can make an analytical calculation, and we can calculate the one particle spectrum that's created when the vacuum is in the incoming modes. And we calculate basically the expectation value in the outgoing modes, and out comes a number of particles. And here, for my explanation, I had very large diagrams with very large changes in refractive index, but here on the right-hand side, I have changes in the refractive index which are much tinier, closer to what can be done in an experiment. So it's of the order of 10 to the minus 6. And we see that the pink region, the peak frequency region, which I identified here as being the sort of black hole-like horizon, becomes a very narrow peak here, in which emission is also peaked. So for actual experimental conditions, we see very nicely that we have a sort of like monotonous background of horizonless emission. And in two specific instances, we have a peak in the emission with a sort of shark fin shape in the emission. And the black hole is really very high, and emission in the negative norm mode in purple and in the positive norm mode, Hawking radiation in green, are actually totally superimposed. So we seem to have very highly correlated emission. And we can, of course, calculate the photon number correlations. So here they are normalized to 1. And we see that, okay, generally we have a background of no emission, and then among certain modes we have some emission, but it's not very highly correlated. And when we have the black hole horizon, we have those two red dots here that are the signature of highly correlated emission among the Hawking radiation, the mode that allows for light to escape from the boundary, and its negative norm part that falls inside. The correlation coefficient is not 100%, it's only 99.3 or something like that, depending on the strength of the change in the refractive index. So we don't have 100% correlation. And in fact, we see that very well because we have non-zero correlations elsewhere. So this is important, you see. This is one first important lesson. It's that even when we have dispersion, we have a horizon, and we see emission that is characteristic of the horizon on top of a monotonous background. And this emission is peaked, and it's also highly correlated. But all other correlations are not zero. So when we have a dispersion model with many output modes, we need to take all correlations into account. And this becomes specifically important when we try to calculate the degree of entanglement amongst the modes, when we try to say how much quantumness there is in those correlations. And so here on the top row, we find the correlations again, and on the bottom row, we have the degree of entanglement that's calculated from the logarithmic negativity. And that's a bit different from what has been done before in analog gravity. So it used to be that people looked at the ratio between the single particle population and the two particle spectra, the correlations to find whether there was entanglement. That's a measure of whether there is entanglement or not. And here with the logarithmic negativity, we are telling how much entanglement there is. So it's like sort of a measure of distillability, if you want. So how entangled exactly is the state, and not just how non-separable is the state. And again, it's the same where we have the black hole. So that's this column here. We have very high degree of entanglement. In fact, the two spectra, they just look very much the same. The degree of entanglement is 98%. So this is very high. We have almost a pure state here, a pure two-mode state at the output. But importantly, at other frequencies where we have no horizon, the degree of entanglement between the states, between the various two modes is not zero. And also where we have a horizon, the degree of entanglement between this outgoing mode, the Hawking radiation, and other modes is also not zero. So there is a certain degree of multipartite entanglement in the optical system. And we can ask ourselves how correlations compare with entanglement exactly. And for each frequency, we can plot the degree of entanglement against the correlation coefficient. So I do this here on a natural scale, and we see that the relationship is not exactly linear. So there is no one-to-one correspondence between entanglements and correlations. And here I just put the entanglement measure the logarithmic negativity on a logarithmic scale to look at the bottom mesh here. And we see that in fact for low correlation coefficients, it's very messy what happens. So it's impossible to tell for low correlation coefficients exactly how much entanglement there is in the correlations. So this is important because this is an effect of dispersion. And because we don't reach 100% entanglement at all, ever, we don't have really a pure state. So we cannot really define a temperature to our state. So there is no notion really of a temperature in a dispersive system. And you might think that this is all due to the sort of model of dispersion which I use. And so I can tell you that this is not the case because it's also the case in the Bose-Einstein condensate experiment, for example. So here we have the very famous picture from the Steiner group where they see two-body correlations. And that's Hawking radiation and its partner. That's a very nice experiment. And the thing is that on this experiment that's published in their 2019 Nature paper, they don't make an entanglement measure. And we know from a lot of theoretical work that just from the correlations, we cannot say that the emission was spontaneous simply because zero temperature and non-zero temperature curves fit the data just as well as one another. So it's impossible to tell whether the temperature was really zero in that experiment. So instead, what we would need to do is to get the particle number and the correlations, and to compute from that a measure of non-separability to say whether the state is entangled, or a measure of entanglement to say how much entanglement there was and how pure the state really is. And this was done in this paper, for example, here by Izoar and Pavlov, and the entanglement is not pure. So there is a high degree of bipartite entanglement, but there are also other modes in the Bose-Einstein condensate. So there is multipartite entanglement. In fact, it's tripartite entanglement. So there are 3 output modes, and they all share entanglement and correlations. So it's an important topic, because here we get really at what we can say about temperature and about entanglement and about non-locality at the output. And really, we would need very complete data sets in order to make full statements. So what I'm just saying, I guess, and this brings me to my conclusion, this is a short presentation, is that because of dispersion, we cannot define a Hawking temperature for the emission simply because the emission changes in characteristics, that's what we saw from the one particle spectrum, as a function of frequency. And it certainly is peaked at the frequency at which there is a horizon. But there it's not fully correlated. And Hawking radiation and its partner are not entangled in a pure state. They are in a mixed state. And this is the case in all analog systems. And one nice way to measure that is to use the logarithmic negativity. So I guess, to me, that poses a question, which is, well, how good are those experiments? And I mean, do we really need to see spontaneous Hawking radiation to make any sort of claim? And I think that we do not need to do that, because as I said at the very beginning of my presentation, we may as well replace the incoming vacuum with a coherent state and outcomes correlated pairs. So for example, Germain Rousseau has shown that in his experiments in water waves, in which he cannot see entanglement, but he can see correlations. And the same token goes for other effects of analog gravity, which are thought of as being classical effects like superradiance or the Penrose process. These are also, I mean, at least for superradiance, they are in nature correlated in their output, and I think there is no problem with observing the sort of stimulated Hawking effect or superradiance. So I think it's fair to say that, and I think we can say that. I think we can say that we have seen the Hawking effect as soon as we have stimulated it and seen the output modes and their correlations. Likewise for the superradiance. But I think that if we want to say that we have seen spontaneous emission, there we really need to use entanglement measures to make a statement and show that we really have entanglement. And again, so far, I think there are no full data sets that can allow us to make this claim. And before I finish my presentation, I would just like to say that there was this conference in London in 2019, and there were many people who wrote conference proceedings after that, and they are all published here at the Philosophical Transactions of the Royal Society. And this is a very nice collection of short articles, and I would advise you to go and read those. Thank you very much.
Thank you very much, Maxime. All right, we will take questions now. As usual, please use the raise hand feature. All right, so Silke. Go ahead.
Maxime. Hi, can you hear me?
Yeah, perfect.
Hi, nice to see you, Maxime. Nice talk.
Thank you.
I was wondering, because when you have the plots with the temperature, where you say you look at the correlations for 0 temperature and then a non-zero temperature, because how much is the difference? I mean, you can never run an experiment at 0 temperature, really. So, but how much?
No, of course not.
So if you look at Jeff's experiments and sort of say how much, you say, if I look at his output and say what is the delta in the temperature away from 0, I can include that, would still be compatible with his measurement. Like looking another way, could you exclude, what temperatures could you exclude given this measurement?
Yes, I can tell you that. So, I mean, it's very clearly written in the Pavlov paper. And I think basically you can include quite a large variation in the temperature and still reflect the experimental result. I'm just seeing that I did my nomenclature wrong, because the red is for temperature equals 0 and the yellow is for temperature non-zero. And just to give you a number, so to give you a number, this temperature non-zero in yellow here is approximately 1.9 times the temperature of Hawking radiation, if that's like the zero temperature.
And what was Jeff saying? What temperature he has in his experiments?
So I think the measurement that Jeff reports is on the static structure factor, and that's in terms of the. I mean, it's a fraction of mc squared, and a very tiny fraction of mc squared. But in that experiment, he doesn't report on the temperature in terms of the Hawking radiation spontaneous temperature.
Thank you. Thank you.
I mean, clearly, I think Jeff's claim is that he has zero temperature in the emission, that he has no thermal fluctuations at the input.
Or he can't see them.
Or he can't see.
It.
Okay.
Yeah.
So, any more questions?
I mean, just so can I comment on this?
Sorry, you haven't finished. My bad. Go ahead.
No, because I mean, it's just not the Jörg is also here. You cannot have it at zero temperature. So it's basically what Jörg said. It's beyond the sensitivity of his detection method. So that should which is confusing. Okay, so but that should also give you some information. No, if you say I have a resolution, because if it would be once it is of a certain temperature, when can I start to see them? That sort of like, it's below my resolution. Does that tell you something about the temperature?
Absolutely. Yeah, I agree with you, and I think it's absolutely fine that it's beyond the detection ability. I think my point here is just to say that if we want to claim that we have spontaneity, spontaneous emission, it being from the vacuum, then we should just make an entanglement measure, and then there is nothing more that can be said, because entanglement can only stem from spontaneous emission.
Yeah, I mean, look, I'm not disagreeing with your statement. One should continue and do further measurements to really establish entanglement. I agree with what you're saying, and basically, I think what we see here is promising, but it's not. It doesn't nail it down. So, and I would agree on.
Yeah. We should push it further.
Yeah, maybe there's also an interesting thing to say. First of all, when you say temperature, if I would only give the license to say somebody's temperature if we measured that the correlation functions look thermal, and correlation functions, I mean not only second order correlators, but high order correlators look thermal. Otherwise, you can say you have a mean energy of my excitations. Or I measure the complete spectrum, or the spectrum is Boltzmannian or Bose-Einstein condensate like, then I can talk about a temperature, because otherwise I might, in these experiments, phonons very little interact. So you might never have a temperature. You might have some kind of generalized Gibbs ensemble type of state in which you are in your initial part, where some modes may be high occupied, other ones may be low occupied. So using temperature, I think, is a dangerous concept. I know it's used extremely hand wavingly, but you have to be very careful to when you say you have a temperature, because it means a specific things from a statistical physics point of view, and also from the experimental point of view. Yeah, and I'm speaking here not as a theorist, I'm speaking as an experimentalist. Yeah. And regarding the role of temperature and spontaneous scattering and non-spontaneous scattering, there are beautiful experiments done in the last 15 years by the Hanover group, and I think also Markus Oberthaler did some of them, but I think the Carsten Klempt and the Hanover group did a lot of beautiful experiments, which were in a different context, but they were looking at pair production by spontaneous emission of pairs by spin changing collisions. And they very clearly see that, you know, if you have some thermal atoms there, if you have some thermal contributions there, how this thing changes or not. And that's basically the same type of physics that you look here.
Yeah, I agree.
Yeah. And there's a whole set of experiments done in the last 15 years about this, how to, you know, where you look at that.
Okay, yeah, I don't know that, but I will look them up certainly. Thanks.
That's you know, Carsten Klempt at the University of Hanover, and there's probably also in some of the experiments from Markus Oberthaler, he discusses that.
Okay.
But I've seen it nicely in Carsten Klempt's experiments, and it's in the very early of their experiments until they managed how to get to a purely spontaneous process, and then they don't talk about it anymore.
I see.
Right. So let's go. We have two hands here. So Cisco, go first. We can go back at the discussion if you want, but let's hear everybody that has a hand up, and then at the end, yeah. Go ahead.
Hi, Cisco.
Hello. I just had a quick question about whether this notion of temperature can be extracted, or is, you know, the relevant one when we have dispersion. Jeff's most recent paper does present results on spontaneous emission, and it seems like they are inferring a Hawking temperature from emission of the spontaneous Hawking radiation using the Stefan-Boltzmann law. Is there a conflict between these points that that Jeff's bringing in, and is this temperature indiscernibility something that's possible to overcome with just slightly more experimental precision, so that you could resolve these, you know, a temperature from these?
Right. I think there are two notions of temperature at stake here. So the first one is sort of the temperature of the condensate itself. I mean, is it very, very cold or not? So do you have solely 0-point fluctuation at the input? So that's the vacuum. Or do you also have thermal fluctuations at the input? And that's what this graph is concerned with here. What I was saying earlier about there not being a single notion of temperature is basically, let me just go back. I mean, whether it's the optical case or the water waves or the Bose-Einstein condensate experiment or the polaritons experiment, we have a dispersion relation. And that dispersion relation is in fact a necessary tool for us, not only because it allows us to contravent the Trans-Planckian problem, but also because it gives us those extra roots on the left-hand side here for me of negative norm, which are necessary to get the AA dagger effect. That's the Hawking effect at the horizon. And the thing is that this dispersion, or those extra roots, they come at the price of all those curves, of all this curvature in the branches. And because of that, if monochromatically, it's certainly possible to say that we have a temperature, it doesn't make sense to define a temperature over a frequency range, unlike for a Planck spectrum, for example. And that's what I'm saying.
Okay. Yeah,
I
was trying to reconcile.
And I think that in his experiment, Jeff usually treats the Bose-Einstein condensate as being totally non-dispersive, although he reports on dispersion measurements. So he considers that the emission spectrum would be flat at all frequencies, which of course cannot be the case. And that's what he means by his Boltzmann temperature. And I think there is a conflict, but it's,
Yeah. I mean, he has a kind of a regime where these effective temperatures look flat and are you know.
And he's solely reporting on the how do you say, on the correlations and not on the spectrum, on the one particle spectrum itself. So we cannot really tell whether it's flat or not.
Oh, I meant his log temperature plot.
Okay. Yes. Okay. Yeah, I'm not sure. I'm not sure about that. Yeah. I really don't know, so I would not want to say something. That's
okay. I mean, of course, he does have, you know, multiple notions of horizons because of the spectrum, and it is I'm still trying to learn exactly what features are rigorously analogous and what features are generalizations that have extra frequency dependence. And anyway, I'm just trying to clarify these little points. Thank you. All right. Next question, Stefano.
I think I have a question that partly was covered by Hannes Jörg, but I'm back to the issue of the temperature. I mean, if you have a Planck distribution, you can distinguish a case in which you have the pairs are entangled with respect to true thermal situation, because basically you have to look at the higher than 2-point correlation functions. Basically, in the thermal case, they're all trivial, and while in the entangled case, so I think I missed the point why you cannot go for this route. I mean, it may be difficult, but what I mean is that why you don't look at higher correlation function, and you should be able to distinguish thermality from the entanglement state.
Well, I mean, certainly I have not done it, so that's the only reason why I did not look there. But it would be very interesting to look into that. And as for the experiments, I don't know how difficult it is truly. For example, in Jeff's situation, to do that. I genuinely don't know. Yeah.
Thank you.
All right. I mean, Silke, I don't know if you have, because you have this pensive face, so maybe you have more questions.
No, I mean, because if you have everything to extracted 2-point correlations, I don't see why you couldn't go to higher correlations. In principle, you should have the data. I mean, Jörg did some correlation measures up to 8s or 10s, I don't know, millions order, and compared it to experiment with theory. So as far as I understand, maybe I'm wrong, I mean, once you have the data, it's just data analysis you need to do, additional data analysis.
Possibly.
Data has to be good enough.
Yeah, I would really not know about the experimental aspects of this. For the Bose-Einstein condensates, I would not know.
Go ahead.
But I mean, certainly one thing is that in most of the data sets that we have for the Bose-Einstein condensates experiments on Hawking radiation, we are missing some data. So we are missing some data already on the single particle spectra. For example, for all the modes, we only have, I mean, in the 2016 paper, we only have the population of one mode. And I guess it is assumed that its partner mode has exactly the same population, and we don't have the population of the third mode. So it's a bit difficult. So the data sets are not fully available.
So I remember that was, again, from an outsider from analog gravity, of course, but I remember in the RQI conference in 2016 that Jeff Steinhauer talked about his 2016 paper. The title was something like Hawking radiation and its entanglement, right? And I remember the discussion with Silke as well. It was long ago though, but he looked at 2-point correlators, right? That's the claim of entanglement was mentioned. That's the key, I guess. That's precisely what you're getting into.
Yes.
That's not enough, right? Is that it?
Yes. So exactly. So this plot here on the left-hand side is a plot from his more recent Nature paper in 2019. Mm-hmm. But he had a similar plot in the 2016 paper. Mm-hmm. The thing is, together with that plot, he also had a plot which showed the single particle spectrum. This is the 2-point correlator at all positions in space. And he also had the single particle spectrum at all positions in space, but for only one of the 3 modes that are output modes in his system. So that's what's missing here to fully determine the entanglement.
Yeah, thanks.
Because basically,
go ahead.
Basically, you have a relationship in the ratio between this single particle spectrum and the correlation spectrum to get a sort of a criterion of non-separability of your state. And that's what he was looking into after the work of Bono Parentani. But yeah, we are missing some further data there to be fully sure.
Yeah, thank you. Very clear answer. And actually, after your talk, I think I have no doubts about it anymore. Are there more questions before we move to the next? Because I'm a bit late, but I like discussions are the best part of a conference.
Yes, they are.
All right, if there aren't any more questions, then let's thank the speaker again. Thank you, Maxime. Great talk.
Thank you very much.
All right, our next speaker today is Roman Rousseau. He's going to tell us about, well, it's the title I can't see right now, but I remember it's Andrew meeting somebody. When Andrew meets, Vasarely. All right, cool. Yeah, sorry about that. I couldn't see the title. Or Transpranckian physics in analog condensed matter systems, dissipation and dispersion. Okay, floor is yours. Whenever you want, 20 minutes, I'll give you a 5-minute warning.
Thank you. I will mostly be a spectator of the meeting between Unruh and Vasarely. So why Vasarely? Because we will speak of correlators between fields in 2 directions, and the pope of correlators and checkerboards is Vasarely, as I will try to demonstrate. So I will rely heavily on the presentation by Stefano and Maxime. So I will skip the basics of analog gravity, just recalling you that Schutzold and Unruh in 2002 have shown that gravity waves in the flowing fluids can be used to simulate phenomena around black holes in laboratory. And this features so-called Beltrami-Laplace equation with the acoustic metrics in the Painlevé-Klustran metric, where we replace the fluid flow velocity by the Newton escape velocity. So, so we can try to reproduce in the laboratory analog black hole flow, like this hydraulic falls here, and cataract, which will be the analogs of analog white hole or fountain. I prefer the term white fountain. So here, I just remind you this acoustic metric, which was derived first by White in 1973. What is interesting is that this acoustic metrics enters into the dispersion relation. And this dispersion relation here, it is written in a 4-dimensional way. But when we write it in a more classical way, you see the Lorentz term and the Doppler shift term, and you can see that the frequency of the wave is modified by this Doppler shifting. And the background, somehow the curved spacetime is hidden in the flow profile, which is U of x in our 1D experiments. So if we solve this dispersion relation, you see that there is 2 signs, plus and minus. So the plus sign, as Maxime has shown, it corresponds to positive energy mode, and the minus sign corresponds to negative energy mode, which will be corresponding to the partners, which is trapped inside the black hole. And as you can see, there is a threshold for the appearance of this negative energy mode when we introduce the Doppler shift, namely when we go into the supersonic region. And we can distinguish subcritical flow from supercritical flow featuring McCone, whereas in subcritical flow, you have essentially subcritical and circular wavefronts. Okay. Contrary to what was discussed by Stefano, here I will break Lorentz invariance by introducing a dispersion, of course, and you see that for usual water waves in the so-called gravity regime, we can have negative energy modes without having transcritical flow. So this is a first departure. Still, we can have so-called dispersive group velocity horizon. And there is an extra feature that I will discuss a lot in this talk, the fact that at 0 frequency, there is new dispersive mode of 0 frequency, which are called 0 mode. And there is the flat free surface, which is a trivial one, but you have 2 modes of opposite wave number and 0 energy. The sign of the relative frequency is very important because it corresponds to when you quantize the fields to the particles for the positive energy wave and the antiparticles for the negative energy waves. And as I said, there is no threshold for the appearance of this wave in the pure gravity case. This is not exactly true in field mechanics because if we introduce, in addition to the first dispersive scale, the water depth, another dispersive scale, which is called the capillary lens, which is controlled by surface tension, you see, a dispersion relation which is much more tricky. And you see we can still have, for example, a dispersive white hole horizon, but we have new dispersive horizon, which I call dispersive blue horizon and negative horizon. And this induces a speed threshold for the appearance of this pair of positive and negative energy modes. And there is also a speed threshold for the appearance of the ondulation. In field mechanics, it is a universal value. It is 23 centimeters per second, which can be computed as a minimum of the phase velocity of gravito-capillary wave, and this corresponds to the so-called Landau speeds for the appearance of these both ondulation and pairs of particles and antiparticles-like modes. So this ondulation is very interesting because it's a classical wave and it can be seen as a kind of Hawking radiation at zero frequency because of the noise. You can have very long wave which stimulate somehow the analog dispersive group velocity horizon. And according to Coutan and Parentani, this zero frequency solution introduce an ondulation of definite and static profile where you recover the wave number kz where omega goes to 0. And these introduce a contribution into the 2-point correlators, here XX prime in the Dirac space, where you have just a product of a cosinus kzx plus a phase times the cosinus kzx prime plus theta. So if you plot this, you have a beautiful pattern in the correlation, the trivial one of the background. So these are some experiments that you can see which were performed in the lab where we measure either in subcritical flow here this zero mode ondulation. So this kind of Hawking radiation at zero frequency. If we focus on an experiment where we remove obstacles, which was not done up to now in analog gravity, we see that if the speed in a water channel becomes superior to 23 centimeters per second, we can observe a spontaneous ondulation, which is formed after a transient, and this is the saturation of the zero mode. So if we look to, with camera on the side, on the space-time diagram of the water depth, h of t of x, we can remove the fluctuation, so we can look to the background, the zero mode, and we can also isolate the fluctuations. We can plot correlations, the trivial one with respect to the background, but also non-trivial one with respect to fluctuations. So first, with the fluctuation, the double Fourier transform of the space-time diagram leads directly to the dispersion relation, where you have the incoming mode, the positive energy mode, and the negative energy mode, and the so-called retrograde mode, which correspond to V mode in the quantum gravity, in classical general relativity context. And what is interesting in this experiment is that as the water channel has a finite width, you see transverse mode in addition. So these transverse modes are akin to massive Hawking radiation when they can be stimulated. So I will come back to this appearance of this transverse mode because they are seen in the correlation map, the trivial one, which is constructed on the mean water depth, here in the Fourier space. So you have the wave number in one direction and the wave number in another direction. And you can see the fundamental mode, 0 plus kz and kz, which describe a 3x3 triptych checkerboard pattern. And in addition, when you introduce the additional transverse mode, you can have another correlations here due to the secondary peaks associated to this transverse mode, massive modes. The direct space correlation is rather boring for the fluctuations. It is more interesting to look at it in the Fourier space. And as you can see, I have superposed here the correlation which is computed from the dispersion relation. Here, for example, you have this kind of patterns that we recovered in our measurements of correlations. So you see the fundamental BN, the cross correlation, which would correspond to Hawking radiation stimulated one if there was a wave maker which was sending waves in this system. Here there is no wave maker. It is a spontaneous noise inside the system which is populating the correlation in the Fourier space. And in addition to this cross correlation, you see secondary lobes, and these secondary lobes correspond to the massive or transverse modes, which are also excited in the system for a reason that I do not understand for the moment. I just present our raw result. And these fundamental mode, as you can see, corresponds to the zero frequency solution. And it is the limit of our measurements that we have performed in 2016, where we are looking to the stimulated Hawking radiation in a subcritical flow. And for a given frequency, the one of the wave maker, we were able to measure this cross correlation. So if this is for a given frequency, which was for this plot 2.5 Hertz, and if you look to the zero frequency limit, it corresponds exactly to this cross correlation which is a signature in the correlation space of the fluctuation of the appearance of the stationary zero mode, which was saturated in fluid mechanics, certainly by nonlinear effects which are controlled by Navier-Stokes equation. And I recall, of course, that Navier-Stokes equation are very different from Einstein equation, but as they are both nonlinear equations, we can imagine that there are some nonlinear scenarios which are able to saturate these growing zero mode. So these checkerboard patterns à la Vasarely can be also now looked at when you add an obstacle which will trigger the first black hole stationary horizon transition with a transcritical flow here and a supercritical flow in red. And then what is interesting is that you have a kind of Transplanckian effect where, because of viscous head losses at microscopic scale, there is a spontaneous transition from supercritical flow towards a subcritical flow, and you recovered again a stationary zero mode or ondulation. But what is interesting with fluid mechanics compared to the Beck case, which was described, for example, by Stefano, is that the ondulation is not inside the cavity between the two horizons, but it is outside the cavity, outside of the in the subcritical region of the white hole flow. So these checkerboards were studied in Beck, for example. There are two types of checkerboards which were reported so far. One which corresponds to the signature of a time-growing dependent growing zero mode, for example, by Fabry et al. Finazzi and Parentini have been looking to equal time correlation function of the density fluctuation in a Beck to try to describe the so-called black hole lasing effect. This black hole lasing effect is due to the fact that you have two horizons and a superluminal dispersion, for example, in the Beck, but it can also be looked at with water waves, where you have either subliminal or sub and superluminal correction. So there are many types of checkerboards in the literatures in analog gravity, and it is complicated so far to understand what is the role of this checkerboard, and are they associated to zero mode or black hole lasing effect, like as discussed by Jeff Steinhauer in 2014, where he was saying that, for example, the band, the escaping flux that we can see here on the top and bottom of the checkerboard will correspond to a kind of Hawking radiation, which is absolutely not clear. But he was already saying that there was also, in addition to the checkerboard, parallel fringe that we can see here close to the white hole horizon. And there has been a lot of debate, so I will not enter into the pros and the cons, but the point is that the fact that apparently his white hole horizon is receding, or at least is moving. If we perform the same kind of simulation in other systems, we recovered these growing checkerboards here, for example, in the work by Yatsuta et al. And often this checkerboard pattern appears as a result of the existence of a cavity between horizons. It is not clear because in the same work, we can see that if the flow is smooth around the horizon, there is no more checkerboard pattern. So is the checkerboard associated to the cavity or not? It is absolutely unclear, at least to me. Other writers recently discussed the fact that in addition to checkerboard vertical and horizontal, you have also a diagonal and anti-diagonal fringe, which are often superposed when you are inside the cavity, where you have a black hole horizon here and a white hole horizon here. So what we did recently is to set up an experiment with a stationary black hole horizon and a receding white hole horizon, a time-dependent one. Initially, we didn't see that this white hole horizon was moving, because if you plot a space-time diagram, for example, in 30 seconds, you see that the horizon is almost at the same position here. But if we make an acquisition for a very long time, we observe that the zero mode was slightly moving. And this will have an impact on the correlation that we measured. First, the usual trivial correlation, the one corresponding to the total depth or the background, namely the zero mode. You recovered now the 3x3 triptych and the checkerboard pattern. And as you can see, there is in the total depth diagonal signal, which correspond to the fluctuating part in the Fourier space. But in addition, which is not trivial, is the fact that also we see that apparently the cross-correlation terms are also populated, which is a little bit strange because it should not normally. And this was also observed in the direct space, where you see the cross correlation in the direct space, either for the total depth you recovered the usual checkerboard pattern here and here. And if you look to the fluctuations, you recovered a checkerboard patterns of the fluctuation of the water depth. So I would like to introduce the name of Vassarellian checkerboards in order to describe them. If we change the amount, if here the color map, we see also a correlation coming from the black hole horizon, which are interacting with the fluctuation and the correlation, but I will not discuss this. It is outside of the scope today. Okay, so Scott Robertson realized recently that when we record for a very long time, there is a slight change of the ondulation, and this slight change of the ondulation, in fact, produce this correlation, because if we average over all the time of the recording or a part of time here, for example, 37 minutes, we observe this correlation, which are populated, but it is a wrong correlation. It is just to the fact that there is a drift of the pattern. If we average,
yeah.
Yes, if we average on the shorter times, we see that the correlation in the fluctuations just disappear. So this is a spurious effect. So experimentalists in nanogravity must be careful. Okay, so some analog space-time oddities. Transplanckian effects may be simulated in analog gravity, as I have seen, by dispersive correction and dissipative effects in classical system. The transition to transcritical white hole flow apparently is triggered by internal dissipation, provided that there is no, for example, gate at the downstream end of the water channel, which would introduce subcritical flow, and then the white hole will be subcritical and located on the top of the water of the obstacle, that as was done, for example, in the experiment of Silke in the Perel of 2011. I have shown also that the Planck scale, namely surface tension, is mimicked by a combination of water depth and capillary lens, which introduce a Landau threshold. So in fluid mechanics, in classical fluid mechanics, Hawking radiation may not reach asymptotic observer because this introduces a blue horizon. So if we stimulate wave with a wave maker, they can produce a pair of analog positive energy and negative energy modes. But these positive and negative energy modes, they want to go at asymptotic infinity, but because of the presence of this Landau threshold, if the speed is not sufficiently strong, then they are blocked again and they not reach asymptotic observer. This Landau threshold also pilot the appearance of this zero mode. So as I've tried to show you today, there are checkerboard patterns at Vassarelli in the correlation maps, and they are studied in analog gravity either to characterize phenomena or to advocate for their own existence. One can distinguish Vassarellian checkerboards due to either zero mode existence, saturated or time dependent, depending if you do experiments or numerical simulations. These checkerboard patterns describe also transverse mode existence, sometimes coupled to zero mode. And there have been attempts to relate these checkerboards à la Vassarelli to black hole lasing existence, at least theoretically. And there is something that I didn't discuss. If the post-processing is not good, for example, if you use rectangular windows with Fourier transform, we can have secondary peaks, as it is well known, and this populates badly the correlation map, so it can be a problem. So this was, of course, dismissed in the experiment I have shown you today. So checkerboards may appear in the correlation maps for fluctuation because of the drift of the zero mode, and this can explain, I think, a little bit of the experiment by Jeff Steinauer in 2014, where his zero mode was not stationary. I will finish by showing you a last effect, last kind of Transplanckian effect due to dispersion and the fact that you have a capillarity. When you stimulate waves, you can have pairs of positive and negative energy mode which are generated at a white hole horizon. And as I have shown you, there is a blue horizon where this Hawking radiation cannot reach infinity, and it is transferred back into superluminal waves, which are capillary waves, which go up the river. And then there is an inverse conversion here, and they can escape from the black hole horizon. So these, of course, are not described by the analogy of Unruh, and we are beyond the robustness of Hawking effect and so on. But I think it is interesting to look to this kind of problem. So theoretically, we can see that the incoming wave on the counter current flow, for example, with the Vancouver obstacle, which was used by Silke van Furtner, we can see this conversion from incoming wave, stimulated incoming mode, to so-called positive energy mode. And then very rapidly, the conversion towards so-called capillary waves, which will be able to go faster than the counterflow. So they will go into what we can call the wormhole, the region between the white hole horizon and the black hole horizon. And because of dispersive effect, then there will be again redshifting, and you can see the wave which are escaping, at least theoretically, and I will show you the experiments now. So first with the wave packet, so we send on the top of an obstacle a very long wave, which will be blocked as a dispersive group velocity horizon of a white hole type. Then it will be converted to what we can call the Hawking radiation, and then Hawking radiation is stopped in this region, and it is converted back into fast capillary waves, which are entering into the forbidden region, namely into the inside of the white hole. So if we do this experiment now, not with a wave packet, with a continuous wave train, you see the dispersive white hole horizon, you see the dispersive blue hole horizon. The medium wave will correspond to Hawking radiation. I must add the fact that the phase velocity is opposite to the group velocity. So even though we stimulate waves which are blocked, the group velocity is going backwards, but here you have the impression that the Hawking wave are going towards the horizon, but it is just the phase that you can see. And as the blue shifted waves are blocked here at the blue horizon, they are converted into very short capillary waves, which are entering into the white hole horizon as a Transplanckian effect. And if you measure this with a laser sheet, here we have removed also the dissipation due to the viscosity. You see the white hole region and the conversion from the stimulated wave towards the capillary waves. So the blue shifting effect, and then another red shifting effect when these capillary waves escape from the dispersive black hole horizon, and they are converted back as analog gravity, as the gravity waves. So as Stephen Hawking said, there is no escape from a black hole in classical theory, but quantum theory enables energy information escape. Translate in field mechanics, capillary system enables energy and information to escape. Thank you.
All right. Thank you very much, Germain. Again, we open the questions now. See the first hand, Silke. Go ahead.
Hi, Germain.
Hello, thank you.
Hi. So I have a question. So you mentioned that in Jeff's experiments with the white black hole horizon, you mentioned that because the horizon is not stationary, you were saying that this could cause the checkerboard pattern. So the first thing, so two things that come to my mind, and I wanted to ask you. So the first thing is, you know, when Jeff measures it, he cannot do a continuous measurement. So he creates a BSC, then he measures, and he keeps doing this for 100,000 times, whatever, hundreds or several hundred times, and then he gets the correlation pattern. And so in this sense, he doesn't have what you have, that the horizon can evolve in time. But I remember we had this discussion in Paris many years ago, where we had this workshop. I think you were there as well. And then Ted Jacobson actually said, maybe from the averaging, because if you average on the horizons are not always on the same point, you could get some effect. Is this the same thing you have in mind?
I think it is different, but what you say is also right. I don't know exactly what Jeff observed. I'm trying to understand. So I'm comparing with the case of the water wave. There is a big difference between the case of Beck and water wave, as you know, is the fact that the ondulation in the Beck is inside the cavity, and in the water wave, it is outside. And then there is the question of, do we have a stationary or moving horizon? And what I have tried to show you today is that there is a contribution of a moving horizon to the correlation map of the fluctuations. This is all what I am saying. The problem is that in this experiment of Jeff, we don't know if these fringe, what we call fringe here, or what is measuring here is a density plot, is corresponding or not to a stationary or time evolving ondulation like the one I am showing you with the water waves. If it is this stationary ondulation which is completely due to the dispersion, then the fact that the horizon is moving apparently will populate the correlation of the fluctuations. This is at least what I'm saying.
I mean, Jeff cannot, no, I mean, they are all destructive measurements, so you cannot follow them. You don't have a time evolution, not in the methods Jeff presented. But then there was what Ted looked at was, because if you superimpose the different simulation, the different experiments, then the undulation is on different locations. And so initially Ted thought that this could really have a big effect. And he mentioned that at a conference, but as far as I know, I looked up the paper later when they published this, right? From the averaging, could you introduce, due to the averaging, a checkerboard pattern or some signal? And I think, I mean, I read the paper and I felt that the statements that were made at the conference were not as, big in the paper. So this is why I thought at the end, it didn't have the big effect that was which initially, Ted had sort of a hint that initially they did some averaging over, I think over just a small amount, 30 trajectories in simulation, a small amount. And I thought this was going away, but it seems to me you're sort of looking at the same effect, but because you have a different system, you can do it in a single shot experiment because you have a time evolution, while here you just compare different trajectories.
So it raises the question of the comparison between all the analog gravity system, where you have ensemble average on one end and time average on the other end. So Jeff is doing ensemble average, and we are making some of the so-called ergodic hypotheses, like in statistical physics, that the ensemble average will correspond to the time average. I don't know if it is true or not. It will be interesting to check these ergodic hypotheses with respect to the plot of the correlation maps that we are looking at.
You should talk to Ted about this. I thought at the end, Ted, I mean, when I read the paper, it wasn't so strong. So I thought at the end, the effect wasn't that big. Maybe we should talk to him.
The fact that Ted is saying that there is an ondulation associated to the white hole, and this ondulation, which is that he calls the bow wave, will stimulate Hawking radiation at the black hole horizon. So in the end, is the white hole horizon of Jeff apparently is not stationary. And I have shown here one experiment where, by chance, we have a very long duration and recording, and there is a slight change and slight moving, slight drift of our white hole horizon, and this apparently populates the correlation map.
I have one more quick question. It's a silly question, but you have this comparison with the artwork, which is very nice artwork. But is there some deeper connection? Is there something, what did the artist really want to depict? Or, I mean, they look a bit similar, okay? So this is nice, of course, but is there some deeper connection you could draw between the artwork and the correlation measures we get, something more time?
I just tried to put names in the many checkerboards I have seen with many patterns and features, and I think there are certainly a geometrical reason why we recovered some similar patterns between arts and science, but it was just to introduce a kind of scientific classification and to put a name. That's all.
Okay, thank you.
All right, thank you very much. Stefano?
Yeah, my question concerns your blue horizon. And I mean, coming from relativity, we are used to the fact that outside of black hole horizons, you can have a potential barrier, and this barrier can basically reflect back waves, for example. So I was wondering if you can connect those, the blue horizon and the red horizon. Probably the one I'm thinking is the most appropriate terminology is the red horizon. From the point of view of the acoustic geometry, I mean, these are frequency dependent, so of course, but imagine at the basic level, if you look at the acoustic geometry, would you have a potential barrier, for example, where there is the red horizon, and then the dispersion would make this barrier basically effective only for some frequency, not for others?
In our last PRL, we have been looking to this case, exactly the one you are discussing. the fact that because of the backscattering or conformal coupling somehow, we can have a partial conversion towards the pairs of positive energy mode and negative energy mode. This is what we have measured in the PRL. The fact that if you stimulate from outside the black hole flow with the stationary black hole horizon, you will have a pair creation, which is not a Hawking process, which is precisely the fact that you have a conformal coupling between co-current wave and countercurrent wave somehow. So I think this is completely different. You have here an effective potential, and this has nothing to do with dispersion. The blue horizon is really the consequences of the existence of a microscopic scale, namely the capillary lens. So this microscopic scale introduces the blue and red horizon, the dispersive blue and red horizon, and this is different from the scattering and the back reaction, the back scattering due to gray body factor, for example. So I distinguished the gray body factors from dispersive effect controlled by microscopic scales, which are different.
Okay, thank you.
All right, thank you. Are there any more questions? Okay, if there aren't any more questions, let's thank the speaker again, Germain. Thank you, great talk.
Thank you. I promise to look to correlation of higher order.
Good. All right, I'm gonna stop the recording for a second. All right, our next speaker is Jose Luis Gauna Reyes from the University of Waterloo, and he's going to talk about gravity through a feedback mechanism. Okay, whenever you're ready, go ahead, please.
Good morning to everyone. Thank you for the invitation. Maybe I will disappoint the analog gravity community gathering in this session because this last talk is not related to analog gravity, but I hope that you like it as well. And so in order to proceed, the talk will be divided into parts. Basically, in the first one, I will review some basic concepts from continuous quantum measurement theory. And in the second part, I will focus on the description and the analysis of two models which implement Newtonian gravity through a continuous measurement and feedback mechanism, the Caffey-Taylor-Mull model and the Tillard-Yoshi model. So in quantum mechanics, it is usually assumed that the measurement process takes place instantaneously. However, there might be some situations in which we will be interested in extracting information from the system while it is being measured. So, and the measurement process takes an appreciable amount of time, t, let's say. So we will be interested in constructing a measurement record for an observable A. And the way to do it basically is the following. One divides the time interval in which the measurement process takes place into infinitesimal intervals of time. From there, one can construct a Gaussian weighted sum of projections onto the eigenstates of the operator. These weighted sums are parameterized by this continuum parameter R. From this, one can construct the corresponding probability density for the measurement. And one can see that, let's say, by analyzing the properties of this probability density, that this measurement record can be regarded as a stochastic quantity, which consists of the following terms. The first term is just the usual expectation of the observable of interest, and the second term is a random term, fully characterized by the Wiener process. The parameter gamma appearing here just quantifies the strength of the measurement. With this idea, one is interested in constructing a stochastic differential equation, which describes the continuous measurement of an observable A. One can find that the corresponding stochastic differential equation is this one, in which one can see that in contrast to standard Schrödinger evolution, this equation is nonlinear due to this the process of this term. One of the main applications of continuous measurement theory is feedback control theory. What's the idea behind this? One has a system that is measured by a measurement device, and the system which is measured is usually called the primary system. The auxiliary system measures the system, but it produces an output which is used to further influence or modify the evolution of the original system, of the primary system. This is the idea behind feedback, to control the evolution of a system. And there are several feedback protocols, and one of the simplest, if not the simplest one, is just easy to Weisman and Milburn. And the idea of this protocol is to simply feedback the system with a measurement record of a given observable multiplied by a Hermitian operator. With this, one can see, or one can derive the corresponding stochastic differential equation that describes the contribution due to the feedback in the total evolution of the system, in which, as we can see, one is explicitly, in a certain sense, coupling the observable which is continuously measured and the observable driving the feedback. Gathering the contributions due to the feedback and due to the continuous measurement that we saw before, one can at the end arrive at the master equation of Weisman and Milburn for Markovian feedback. We see that this master equation leads to the coherence effects both at the level of the observable, which is continuously measured, and at the level of the observable driving the feedback. And thus far, I haven't said anything regarding what happens if, in addition to this continuous measurement, the system is evolving or is subjected to an evolution encoded in a Hamiltonian operator H. The total master equation will just be obtained by adding the Schrödinger evolution to this contribution. One of the advantages of this Weisman and Milburn master equation is that it can be generalized to a set of observables which are continuously measured as long as the noises are independent, and as we will see, it can be generalized as well to observables which are defined at each point of a space. So with this idea in mind, we will study now some models which implemented Newtonian gravity through this continuous measurement and feedback mechanism. First, a little bit of motivation. Perhaps one of the greatest, if not the greatest open problem in physics is the construction of a quantum theory of gravity. I think it is safe to say that the lack of a universally accepted and experimentally falsifiable theory has led some people to question if the quantization of gravity is necessary at all. And in this line of research, some people have devoted to the construction of hybrid classical quantum dynamical models, which may be experimentally falsifiable. So along this line of research, in 2014, Caffrey, Taylor, and Milburn proposed a model which consists of the following scenario. So imagine that you have two particles which are oscillating and which are interacting via the standard Newtonian gravitational interaction. The initial distance between the particles, let's call it d, is much greater than the displacement from the equilibrium positions of each of the two particles. So after, let's say, Taylor expanding gravitational interaction and quantizing the system, one arrives at the Hamiltonian of two uncoupled harmonic oscillators, one for each particle, and a coupling term which encodes the gravitational effects, as this constant k is directly proportional to the masses of the particles into constant, and inversely proportional to the distance d, to the cube of the distance d between the particles. So the proposal of Caffrey, Taylor, and Milburn was to replace this, let's say, standard, let's call it gravitational Hamiltonian, to recover it at the level of the master equation. How did they do that? Well, they proposed to continually measure the positions of the two particles. So as we saw before, then the measurement record will be constructed through the expectation value of the position of each of the particles plus the corresponding noise. From this, they consider, instead of this gravitational Hamiltonian, the following feedback Hamiltonian. The parameters, constants chi1, 2, and chi2, 1 are just parameters of the model, which are later to be fixed. And we see here the key element. So we see here that the position of particle 2 is influenced by the measurement record of particle 1, and vice versa. The position of particle 1 is influenced by the measurement record of particle 2. So by following the standard continuous measurement and feedback theory that we saw before, one arrives at the following master equation. So we see indeed that they recovered the let's say the full Hamiltonian, the part of the oscillators, and the linearized gravitational term. But the price to pay in order to recover this term is the inclusion of some terms which lead to the coherence effects. The parameters gamma, which, as I said, quantify the strength of the measurement, are also phenomenological parameters of the model, and under some conditions they can be minimized. For example, if one assumes that the masses are equal, they can be minimized, and this can be experimentally tested. So as you see, this model is a model that implements a linearized gravitational interaction through this mechanism. So there were some questions at the time, which include the following. The first one is if this model can be generalized to more than 2 particles for a system of point-like particles, let's say, for simplicity. And the other one is if one can implement, instead of a linearized gravitational interaction, a full Newtonian gravitational interaction. So Altamirano and her colleagues in 2018, they proposed a pairwise generalization of the KTM model. In this generalization, the idea is the following. So I just here illustrated for the case of 3 particles. The measurement records will link the particles in pairs. So for example, for a given particle, each of the other particles will measure the position of each particle. So we can write it down. Let's say the corresponding measurement records. The index alpha indicates the particle which is measured, and the index beta indicates the particle performing the measurement. So with this idea and implementing a linearized gravitational interaction in which, by construction, we neglect self-interactions between the constituents of the system, which is nothing unusual, one can arrive at a master equation which recovers the linearized gravitational interaction. And in this case, we have, as expected, some decoherence effects, which will depend, of course, on the explicit values of the phenomenological parameters. Notice here that in this approach of generalizing the KTM model, the particles, the decoherence effects do not mix different particles. It was found out that this model was ruled out through comparison with interferometric experiments. So the question is was this the only way to generalize the KTM model? Is there another, let's say, in principle, plausible mechanism of generalizing it? And the answer, in principle, will be yes. So we propose another generalization of the KTM model, in which, instead of having measurement records that link the particles in pairs, one has a single measurement record for each particle. No? In this case, this prescription also leads to a master equation that can recover the gravitational interaction. And in this case, if you notice, of course, that for n equal to 2, this model recovers the original KTM model, sorry. But for n, the number of particles greater than 2, the decoherence terms mix different particles. This is an important characteristic of this model, which actually makes it physically inconsistent for the following reason. So imagine now that you have 2 composite systems, one of them constituted by n1 constituents and the other one by n2 constituents. If now, let's say, one would like to describe the dynamics of the system in terms of the center of mass, and one would expect to recover to these composite systems the master equation for 2 particles and the original KTM model. It turns out that when tracing over the relative degrees of freedom, terms which mix the center of mass operators of the 2 composite systems survive, because in general they are not non-vanishing, and therefore, and this does not happen in the 2 particle case. Therefore, this model is theoretically inconsistent. So, say thus far, we have seen that the 2 plausible generalizations of the KTM model are either experimentally or theoretically ruled out. But the question is, if maybe we are missing some information due to the fact that we are linearized in the gravitational interaction, is it possible to save a full Newtonian interaction model? And the answer is yes, actually. So some years later, Tilva and Yoshi propose the following scenario. Instead, first of all, they consider a full Newtonian gravitational interaction, and then instead of measuring the positions of the particles, they measure the mass density of the system. So they defined a measurement record at each point of the space Well, as usual, one has expectation value of the observable measure, in this case, the mass density of the system, and the random term. In this case, the noise is correlated through gamma, the inverse kernel of what is appearing here in the expression for the measurement record. So the idea is that, let's say, just to try to have some idea, that is there is some kind of a detector at each point of a space which measures if there is a particle or not. No? So at the level of the feedback interaction, one considers the following feedback, which, as we can see, is also of the Weismann minimal form, as it is just the product of the measurement record times a Hermitian observable. With this prescription, and just, let's say, following a straightforward extension of the theory contest measurements just for an observable defined at each point of a space, one arrives at the following master equation, in which they also recover now a full gravitational interaction, and the corresponding decoherence effects are encoded in this decoherence kernel D, where the first term comes from the continuous measurement of the mass density, and the second term comes from the implementation of Newtonian gravity through a feedback. Now, in analogy with the KTM model, the decoherence effects in the Tilda-Yoshi model can be minimized with the following choice for the correlation kernel gamma, which is basically proportional to the full Newtonian interaction. With this prescription, one arrives at a decoherence rate, which is basically that of the Yoshi-Penrose model. So this Yoshi-Penrose model is already well known to suffer from divergences unless a regularization mechanism is proposed, and therefore, let's say this model also diverges unless one implements a regularization mechanism. The idea is the following. So one is considers a smearing function G that acts on both the Newtonian kernel and the correlation kernel. This is formally equivalent to smearing the mass density of the system. So the physical idea, let's say, coming back to a scenario of point-like particles, is the following. Imagine you have a system of point-like particles interacting just through the standard Newtonian gravitational interaction. So with this prescription, one has to quit on one of two ideas. Either that the force is given exactly by the standard Newtonian expression, or that one has point-like particles. Just for the purposes of simplicity, we will stick with the notion of point-like particles and modify the Newtonian interaction. So the question is now, well, we saw that the KTM model is ruled out. And the question is if something similar happens with the Tilda-Yoshi model, because as both models implement Newtonian gravity through a feedback mechanism, one may ask if one is not a limiting case of the other, or what is happening here. So if one can do the comparison also with the universal generalization. I just put here the pairwise one for simplicity. So if one simplifies, or let's say approximates the Tilda-Yoshi model to a linearized regime of gravity, one finds out that the decoherence effects predicted by these models are fundamentally different. And therefore, despite the fact that,
5 minutes more.
Okay, despite the fact that the Tilda-Yoshi the KTM model is discarded, the Tilda-Yoshi model cannot be discarded, let's say, by the same arguments. And finally, an interesting question to ask is if there are other scenarios in which one can implement a full Newtonian gravitational interaction in addition to the Tilda-Yoshi model. So let us come back to the point-like picture, let's say. So one would have that after neglecting the same interaction, the gravitational interaction would look something like this, let's say. And one would be interested in implementing this this continuous measurement feedback mechanism. It is not clear how to proceed here, but let us suppose that the measurement record would be implemented in some way like this. It has to be something similar to this. The particular form of the structure of the Hamiltonian, in particular, the particular structure of the non-linearity of the measurement record with respect to the feedback Hamiltonian, does not allow to implement the Weismann-Minwood protocol. So I'm not saying that there are no feedback protocols that may eventually be implemented to achieve a full Newtonian gravity, but at least the Weismann-Minwood feedback seems ruled out for the position. So the other option is to measure the mass density of the model. In this case, one can implement a pairwise approach in which, as said before, the measurement record links the particle in pairs, the one measure and the one performing the measurement. One arrives at a master equation which recovers linearized, which recovers full gravity, sorry, and the corresponding coherence effects appear as well. But this model is also inconsistent because imagine now that we have the interaction between a system constituted by only one particle and a system constituted by N2 with N2 an arbitrary number of particles. It turns out that when tracing out over the degrees of freedom of the second system, the coherence decays at a rate which is proportional to the number of particles of the second system. This is an unphysical result because the number of particles of the second system might be arbitrary. No? So it would lead to basically infinite coherence decay rates. So in summary, we studied two models. We studied the relations between them and found out that for, let's say, the two take-home messages are the following. The first one is that the Tilbat-Yoshi model is not a generalization of the KTM model. There are two fundamentally different models. And the second message is that at least, let's say, within a Weismann-Mirburn prescription, the Tilbat-Yoshi model seems to be the only natural way to implement a full internal gravitational interaction. And with this, I finish. And just if I may quickly add something which is non-physics related, but which I find something very interesting. I don't know if maybe you share this opinion or not, that in recent years, let's say, historical revisionism has gathered force in every country. Like, for example, now in France, I think there's a hot debate regarding how to study the figure of Napoleon. And for example, in my country, Mexico, in this year, we are commemorating the 500th anniversary of the fall of Tenochtitlan, the capital of the Aztec Empire. So nowadays, there's a hot debate of how to define it as an invasion, as a rebellion, as a conquest, something like that. So I just wanted to say that there's a place in Mexico City, which is not as a square of the three cultures. As you can see, the pre-Hispanic culture, the Spanish culture, let's say, and the more modern culture, in which there is a plaque which perhaps provides an answer to this, is saying that the fall of this empire was neither a triumph nor a defeat, but it was just the painful birth of the people that constitutes now Mexico. Thank you very much.
Thank you very much, Mr. Luis, both for the physics and the and the commemoration of the story of the Mexicas. Very nice. All right, so we open the floor for questions. Please raise your hands. Okay, Cisco, go ahead.
I just had a very quick question about the unphysical result that you mentioned. Could you elaborate very slowly? Could you possibly please go back to that slide just for a moment?
This one, huh? Or which one?
Yes, this is the one. So is this like the collective decohering caused by the rest of the gravitational environment around it? So,
yes, basically one is let's say studying interaction between a system which happens to be formed by only one constituent, and then with an arbitrary other system, no? And then let's say, and then if one, let's say, just works in Fourier space, traces over the degrees of freedom of the second system, then one finds that the coherence rate of the system basically follows this expression, or is given by this expression, which explicitly depends on the number of constituents of the second system. And let's say, in principle.
So for instance, the decoherence rate is dependent on the curvature or something like this, so which immediately doesn't seem unphysical. What exactly about this do you find unphysical? Is it incompatible with our observations of how particles behave around other?
I think that the physical aspect is that basically it scales with the number of constituents, no? So it may lead to arbitrarily high coherence decay rates. So for example, the Tilbat-Yoshi model.
Is that independent of the size?
In addition, let's say, yes. It only depends on the number of constituents, yes.
Oh, and not on the size. Oh, okay, okay. I absolutely agree. That seems
so. Because let's say if somehow it was also scaled with the size, then one would perhaps say, okay, so maybe it compensates in some way the expression, but no, it only depends on the number of constituents, because let's say this other factor sigma, which I did not explain, is just the smearing of the Gaussian function, which has, let's say, nothing to do with the constituents of the other system. No? So just, let's say, now that you mentioned this point, for the sake of completeness, in the Tilladioshi model, one finds that also using a similar expression, that the coherence rate decays basically at the expression, which is basically this, except for this factor of n2. So, which makes it consistent, no? Because it does not depend on the number of constituents of the resistance. Yes, it only depends on the mass of the person.
Yeah.
Mm-hmm.
Yeah. I mean, I would expect it to depend on, you know, if your gravitational interaction is inducing a decoherence effect on your subsystem, you would expect some dependence. But if you can make your system arbitrarily dilute and get the same decay rate, that seems like it would be kind of unphysical. So thank you for that clarification.
All right, thank you very much. We have another question, Benito.
Hi, can you hear me?
Yes.
Okay. Well, thanks. Very nice. So one of the things that I always find puzzling about these models of Newtonian quantum mechanics kind of stuff is, you know, for instance, how fundamental a role things like the number of particles plays in the models, and you see, we know in quantum field theory that number of particles are these kind of I guess this kind of observables is not really fundamental. I don't know if could you say something about this?
Well, let's say, I think what can I say is the following, that at least for the case of the Tilladioshi model, the choice of the mass density as the observable which is measured is a very convenient choice, because let's say the mass density allows to work in a second quantization language, also allows us to treat, in the case of identical particles. And let's say from my point of view, I think that let's say no one expects this, I think, or at least no one expects this to be a fundamental model, but only just to give some light about how to merge, let's say, gravity and quantum mechanics within a single framework. So let's say I would keep it that way. Let's say historically, the Dioschi-Penrose model was introduced. Let's say the stochastic differential equation for the wave function was just derived by some heuristical arguments, but really there was nothing fundamental, or let's say it was just postulated basically for practical purposes. But another say advantage that I see from this Tilladioshi model in particular is that it provides a derivation, if you want to say it like that, to the Dioschi-Penrose model, because the Dioschi-Penrose model is just the particular case of the Tilladioshi model in which gamma is said to be equal to minus twice h bar the gravitational interaction. So it gives a more robust derivation of this kind of models. I'm not saying that perhaps eventually they will be discarded or not, but at least from a theoretical point of view, there is a more solid background to, let's say, it's not that, let's say my main take-home message would be that it is important to take, or not important, but I say it is interesting to take, to pay attention to these kind of models, no? Because they are not as, let's say, taken out of nowhere as they originally seem, no? To let's say.
Yeah, no, I definitely agree with you that one should pay attention to these models. My remark was more in the direction of, well, there should be also some effort put into making some covariant, you know, fully quantum field theoretic versions of these models, particularly in the context of semi-classical gravity.
Okay. So regarding that aspect, I think that the main problem, let's say, as far as I know, actually there is not a universal theory that extends continuous measurements to a relativistic setting, because for example, in this case, this presentation was based on Gaussian continuous measurements, which are defined in terms of the Wiener process. So already there are problems in defining a Wiener process in a relativistic setting. So let's say, I would guess that, I mean, I'm not saying that it's easy, and let's say people have worked on that in parallel. Let's say, for example, there are some, I don't know if you have heard, there are some models which were historically introduced as modifications to the Schrödinger evolution that are called dynamical collapse models. These models were thought to be, or are thought to be, say, phenomenically different from the standard Schrödinger evolution, but it can be seen that they can be encoded, at least the more robust of them, they can be encoded within quantum continuous measurement theory. But the question is that, let's say, they have worked, let's say, separately from this in trying to derive relativistic generalizations of these models, and so far the first models were derived in the late 80s, and so far they haven't succeeded because actually they face exactly the same problems here, and let's say it is not trivial at all to derive to try to derive this generalization. No, it may be possible that perhaps for a certain kind of observables, these generalizations may not be plausible or not, but let's say, I think that is, in order to answer that question, one would need to address how to generalize continuous measurement within a relativistic setting, and the work done so far is, let's say, very limited.
Okay, thank you.
Before we go to Cisco, I have a quick comment on this. There's something, if that's okay, Cisco. I don't know. I mean, I don't know if you, because you seem, maybe you want to say something super relevant to what we said.
Sorry, it was exactly about this, but if you wanted to talk about something
please,
exactly about this also.
Yeah, I also talk about this, but yeah, go ahead, please. Yeah.
Thank you very much. It came to mind, this approach coming from the corrections to a path integral iterative solution to canonical quantum gravity, where you get like the next correction to the semi-classical Einstein equations. It gives you something that if has a path integral representation that makes it look like you're giving stochastic fluctuations to your space-time from the back reaction from the matter. This has been used kind of to attempt to do the same kind of continuous measurement that Dioschi and Penrose are kind of playing around with, well, mostly Dioschi. And that's one possible framework that people have done some work in there. Baylock, Hugh in particular, has a lot of thorough treatments of the structures that resulting Einstein-Langevin equation, for instance. So if someone was interested in kind of merging these, I feel like that, some of the pieces are already there.
Okay, thanks.
Right. So
just sorry to interrupt. Like, I think that everyone should be interested in trying to, well, let's say, of course, everyone works in their own area, but let's say, as I said, I think, or in my opinion, this is perhaps one of the most, if not the most important open problem. No?
Yeah. It's a
Cisco, you mean stochastic gravity is what you were referring to? Is that it?
Yeah, but not necessarily. I mean, when people say stochastic gravity, they often include some sort of fundamental postulate of stochastic structure. The stochastic structure I was talking about from the coming from canonical quantum gravity is just an effective stochastic structure. It's talked about in Kiefer's quantum gravity textbook for one thing, but it's basically just reinterpreting the structure that you get from corrections to the semi-classical Einstein equations, reinterpreting it in terms of the path integral for a stochastic variable. And so you're not actually postulating it. It's just the next correction in a path integral treatment of basically trying to solve the Wheeler-DeWitt equation. So that's a kind of way where you can kind of bootstrap this idea directly from quantum gravity in a covariant way. So I think this may have been related to the idea that you're suggesting, to try and make it a relativistic treatment. And it also has the added bonus of getting pulled right out of the theory itself, just from what we know about canonical quantum gravity, which, albeit, is not that much.
Okay. Okay, thanks.
Just to comment on, I mean, the stochastic gravity you were mentioned that where Balog and collaborators have worked on. I mean, that one, you can also, on the one hand, you can show maybe similar to the canonical treatment you are referring to, not maybe, might be related, but in a more covariant, not canonical treatment, but you can show in fact that that's equivalent to what you would get for the quantum correlation functions if you were doing a perturbative quantum gravity. However, so meaning that you can calculate correlation functions with stochastic gravity, and it's equivalent to the result you would get in perturbative quantum gravity if you use a 1/n expansion to the Gaussian level. Then if you go to higher orders, this would coincide with a perturbative quantum gravity calculation over non-trivial backgrounds up to a certain order. The natural way of organizing it is 1/n expansion, but it's a sort of Gaussian. However, it's true that you could take that mathematical stochastic framework, forget about this question, you know, as a sort of approximation to perturbative quantum gravity, and just take that as a mathematical construct. In a sense, it's a little bit similar to the idea that if you look at some of these models, like the Dioschi-Penrose model, some of these things you are mentioning here, you have a master equation here. If you were considering an open quantum system where everything is standard quantum mechanics, you could also derive, you know, similar master equations. The difference is that the Dioschi-Penrose model or some of these, you know, dynamical collapse models and so on, is that it's not that it's coming from an open quantum system which follows standard quantum mechanics. Is that you don't have an environment, let's say, and you think that there's some kind of fundamental, non-trivial at the fundamental underlying level that is giving rise to that, and that takes you beyond quantum mechanics. So in that sense, maybe one could use some of the structures that one finds in the traditional approach to stochastic gravity and try to then do something similar, as you are suggesting, Cisco. So it was just to clarify that the way some of us working on stochastic gravity thought about it, we saw that it was just a convenient way of doing calculations. You could interpret it at least that way with standard perturbative quantum gravity. But you can take that mathematical structure and try to pursue something, as you were suggesting, similar to looking at, as I was saying, to master equations you get in standard quantum mechanics for open systems, and instead, you know, trying to see whether you can derive that from a case where you assume that this decoherence is coming from a fundamental underlying level, not from an open system that you're tracing out.
All right, thank you. Yeah, some of the things I want to say have been said already by Albert, which I was about to say. Yeah, maybe Albert is the person who should say it. So yeah, very nice. I have one question about these models, right? I mean, there's something that I never liked about the Dioschi models. I mean, all the generations of Dioschi models. So imagine that we had no idea how electromagnetism works, and we just see Coulomb charges, you know, Coulomb potentials, and we have no idea how that works. And imagine we don't know how to quantize that interaction. I mean, we actually do, but imagine we didn't. Somebody could say, but we can look at the Coulomb potential and do this kind of treatment the same way. And then they would discover, actually, that was all wrong because we can do it properly. And this model is definitely not equivalent to quantum electrodynamics. Isn't that kind of like some evidence towards saying, why would you expect it to work for gravity, though, if already for something like electrodynamics doesn't give you the quantum structure what it's behind? I don't know. I mean, what's the difference? Maybe I'm missing something, but because they usually look at Newtonian gravity and they look at Newtonian potentials. Somebody could have said the same about the electromagnetic interaction. So what's the difference in these models? What makes it, why are they treated seriously when we know for something very similar, which is the Coulomb potential, it wouldn't work? I wonder. I mean, I know there's some differences, right? But I want to know if there's a key difference that makes it more interesting to look at in the case of gravity.
Well, let's say let's say what I would say is that okay, let's say I think that situation that you imagine that you didn't have an electric basically quantum electrodynamics is of course it's a good exercise, but it's also kind of tricky in the sense that it does not take into account basically the historical evolution of, let's say, the description of the merging between quantum mechanics and gravity, no? In the sense that so but from my point of view, all these models emerge because thus far the theories that have been proposed are either or just can be regarded only as effective theories or suffer from some other inconsistencies. So I would agree with you that perhaps this is not of course, I think no one expects this to be a fundamental model, but let's say for me the attractive appealings of this model is that they are in principle experimentally falsifiable, and that at least let's say if eventually ruled out, which might be the case actually, at least I think that in doing so they will provide us with some information about how gravity and quantum mechanics are related. No, let's say in that sense, yes, I wouldn't, let's say, be I would take this model also with some caution, but I think anyways that it is interesting to see how far we can push these ideas, no?
Because it's different, right, from if we go to passive quantum gravity or statistical models, like all those things, as Albert was saying, right, is basically going from first principles and writing a stochastic theory with a minimal amount of assumptions. Basically, the assumptions are some assumptions on the statistics of what's going on. When can I take my expectation values, basically, at what time in the dynamics can I? But I guess one could do something like this on these other models, right? I mean, again, taking it as a fundamental stochastic theory. I guess my problem is not with the philosophy behind it; it's with these models in particular. That I don't know why they are that. I mean, again, this could be perfectly well ignorant. Oh, Cisco may have the answer too. Could be ignorance on my side too. Maybe Cisco, go ahead.
Penrose was one of the first to point out exactly why it was fundamentally different in a gravitational setting.
Go ahead, please.
From an electromagnetic thing. The argument that Penrose makes is based on time evolution vectors, basically killing vectors of different spacetimes, and how if you have a superposition of different states that correspond to different geometries, if they have each individual notions of time evolution that are sufficiently different, then it will induce either a decoherence or a collapse effect in the superposition, just because their time coordinates no longer march in phase with each other. So that the superposition structure, the interference gets wiped out between them. This was the basic argument that came out of Penrose and Dioshi's ongoing discussions about this, and it gave a little bit of justification for the Dioshi model, or more like motivation. The suggestion I made earlier was about trying to connect these, because instead of thinking of this as a fundamental model, it could actually be fundamental but derived from a fundamental quantum gravity model, like for instance the stochastic structure from back reaction corrections in perturbative expansions in quantum gravity. You could use that structure to derive this fundamental decoherence effect in a Newtonian setting. So,
but in the Dioshi,
there's a reason that they're different. Sorry,
yeah,
go on.
I agree with you that would be a reason they're different. I don't see that reason here in these models. They're considering Newtonian potential, right? There's no structure, superposition structure for time evolution here.
Penrose derives the exact same expression just by comparing accelerations of two different spacetimes, and you can interpret that expression for the decoherence rate in terms of the difference in self-energies of two different mass distributions corresponding to two different elements of a superposition. And the farther they get away from each other, the higher the decoherence rate is. So you can interpret those elements in all of those expressions that Dioshi uses. Anyway, so I think there's a conceptual reason why it does make, it's more motivated in a gravitational setting. It has an interpretation that,
I mean, I think also that it's even for Dioshi originally, which is maybe the reasoning was less sophisticated as what you were indicating for Penrose. It's that the motivation is really this dynamical collapse model. So, this issue with the unitarity of gravity when you go in the macroscopic regime and all these, paradoxes or these questions. So those pursuing this idea of kind of dynamical collapse. So I think that the motivation behind Dioshi was that you know, you want to have something that where this dynamical collapse becomes more important for macroscopic objects, in a way in which you have something that is universally bigger for macroscopic objects is not so much electric charge, for example, but masses. And so I think that that was partly the motivation, you know, looking for some kind of collapse models beyond quantum mechanics. And then why masses should play a role, I think that the reasoning was a little bit this one, which is that mass is something that, and the gravitational interaction, is something that, you know, is sort of universally grows for, or is universally large for macroscopic objects, the more macroscopic you are. So I think that that was perhaps some of the motivations back then, you know, in the 80s in looking
absolutely for specifically for Diosha. I find that that motivation a bit less compelling, but yeah, absolutely.
I'm not trying to defend this. I'm just trying to present how I think their motivation was. Yeah.
I mean, just to add to it, I mean, this all has to do with the measurement problem. To be, I mean, this was the central motivation of Giossi and of many other people that started developing this, like Girardi and so on, that dynamical reduction models. It's to do this whole idea of having something special about microscopic objects has to do with the measurement problem and on why, you know, emergence of classicality in a sense, why our apparati of measurement are not in superpositions or things like that. And
I agree with that, but well, you see, this is not only gravity. You could apply this. You can talk about continuous measurement in non-interactions, right? That's what I'm saying. And if you are going to stay, I hear the motivations, and I understand them. But if you're going to stay at the level of Newtonian potential, you're not going to see any difference. Go ahead.
No, but Eduardo, there's another. It's hard to get a word in edgewise here. I mean, one of the key differences in a simple way is you can't shield gravity. Unlike the other forces, you can obtain neutrality, but there's no such thing as gravitational neutrality. And so this leads to the notion that gravity in some sense is continuously measuring things. How it works, of course, is a very open question. But that's my understanding of at least the more recent motivations for doing this without digging back 30 some odd years ago or whenever it was, 40 years ago.
So, sorry, what was, Rob, can you repeat the argument?
Well, simply that the other forces of nature can be made neutral. You can, it's possible to shield such interactions, but you can't do that with gravity. It's cumulative to the best of our knowledge, and you can't, there's no such thing as a gravitational shield. So the idea is gravity is all pervasive and effectively is an environment you can just never get rid of or even minimize. And so the idea is that gravity in some sense is effectively measuring other systems and might emerge that way. Whether that's a great motivation or not, I don't know, but it's a reason. I mean, gravity is different from the other forces in that regard.
Yeah, so I guess that's what I'm trying to ask, like, where in this model can I see that there's a justified difference if you are going to stay at the level of a Newtonian potential, right? Not to do the same with a Coulomb potential. I mean, that's definitely a difference, I agree, yeah. So at this point, if you have more points, I mean, you can bring them up. Discussion. Yeah.
I wanted to add to the whole discussion of whether this comes from quantum gravity or it comes from elsewhere and so on. And one point I think that is one point at which it's worth separating, you know, this continuous measurement models from just something coming from quantum gravity, is that if you can imagine that we have a theory of quantum gravity, that, you know, we have, you know, fully exact correct theory of quantum gravity, this doesn't mean still that questions such as the you know, measurement problem are resolved, because if this is standard quantum theory, quantum gravity will continue to have the measurement problem in itself. So in a sense, you know, it is also kind of attractive to think that, well, perhaps these two problems can be resolved simultaneously. You know, that gravity is special, it has to do with this measurement problem and so on. And well, these models are obviously just some games, you know, some toy models, but as Jose Luis was pointing out, I think that they are interesting. They're definitely, they try to address things in in ways that are more precise than just saying a few words and some flashy arguments without any maths. So I think this is interesting.
Yes, Hans has a hand in the discussion, I think.
Yeah, I mean, I have maybe one comment on that. I don't think that I think you have to separate these problems because, in experiments in the last 15 years, we had shown that how basically classical physics and classical statistical mechanics very naturally evolves from the unitary evolution of quantum mechanics in our experiments, and how basically showing that you have a generalized a Gibbs ensemble and a classical statistical physics ensemble and a classical density matrix doesn't tell you anything if quantum mechanics lives or is dead. And this is a series of papers from the studying from the way of how generalized statistical ensembles emerge to our recent Gaussification and recurrence papers, and that basically that the emergence of classical world is completely independent from the quantum measurement problem. That's experimental fact by now. If you look at the many bodies at many body quantum physics. And so one has to state that you have to be careful of that how to relate that. The other problem is a fantastic, interesting problem. But if you only are interested in emergence of classicality and the classical world, you don't need any of that. You don't need any detector, you need any observer, anything. You just need a very careful analysis of complexity. And you can show that experimentally.
So sorry, what's the standard reference for this that you're mentioning?
That's our series of papers on non-equilibrium dynamics and realization, starting from the pre-summarization paper in 2012, the light cone emergence of a decoherent state, the generalized Gibbs ensemble, the correlation function papers, the recurrence paper, the emergence of recurrences, and the last paper just came was in Nature Physics a few months ago, which was basically how a very strongly correlated system becomes Gaussian. And then if you set up the experiment correctly, all the very strong quantum correlations can come back. And in between, you have a classical density matrix that is undistinguishable from any classical state.
Okay. I'm going to do a quick check though, because there's still some hands up, just to make sure. So Rob, do you have points to make?
Well, I said it earlier about the shielding. That's fine. I should take my hand down.
No, that's fantastic. That's a very, very good point. I like that. Yeah.
Cisco, do you have more? Okay, no, the hand just went down.
Yeah. Oh, sorry. Yeah, I was just kind of responding to Georg's comment. You're basically distinguishing between like a measurement that's interpreted as like a collapse and just emergence of classicality from decoherence, right? This is the experimental fact that has been established.
From information flow, yeah. From information flow, yes.
Okay.
So the emergence of classicality, you don't need any, I think that these are separate problems. They are, if you look at very simple systems like a single photon on a beam splitter, then I think you're missing most of the interesting physics. And then you come to all these paradoxes.
Yeah, this is still a controversial thing about which way to go with these collapse models or gravitational fundamental gravitational decoherence, because Diyoshi in this model, it's effectively a collapse measurement induced by gravity. It's also possible that you just get some dephasing and gravity scrambles your information without collapsing it, more like a traditional decoherence effect. So yeah, everyone's still trying to untangle these things. It's unclear if they could be just separated or how they should be separated.
All right, are there any more questions, things to add to this discussion? or any other questions related to the talk? All right. Okay, well, if there are no more questions, let's thank again Jose Luis. Thank you very much. Let's thank all the speakers of the session. It was a great session with a lot of discussion. I really appreciate these times. All right, so before we finish, let me just remind you, next week, I think Europe catches up with daylight savings time. So we will go back to the usual, for those of you not in North America, I guess, I don't know how the rest of the world does it. I know about Europe and North America. I don't know about the rest of the world, but to keep that in mind, if you are changing to daylight savings time, then we will go back to the previous schedule. Okay. Other than that, thank you very much for coming. Very interesting session, and I'll see you again next week. Thank you, everybody. Bye-bye.